Good morning. Professor Peter Stich, President of Slovenian Academy of Sciences and Arts. Professor Klaus Mainzer, President of European Academy of Sciences and Arts. Professor Felix Unger, the Honorary President of European Academy of Sciences and Arts. Ladies and gentlemen, it is my special pleasure and privilege to open the 12th Danubian Conference organized by Slovenian Academy of Sciences and Arts and European Academy of Sciences and Arts, taking place these days in Ljubljana. On behalf of the organizing committee, I would like to express best wishes for a scientifically productive conference and a socially enjoyable stay in Ljubljana. And now I would like to invite Professor Peter Stich, President of Slovenian Academy of Sciences and Arts, to give the opening address.
Dear Professor Unger, the Honorary President of the European Academy, dear Professor Mainzer, the President of the European Academy, Professor Knežević and Vukčević, President of the Serbian and Montenegrin Academy of Science and Arts, Professor Toplak, the President of Alma Mater Europea, esteemed participants, dear colleagues, ladies and gentlemen. It is my pleasure to welcome you at the 12th Danube Academy's conference in Ljubljana and at the Slovenian Academy of Sciences and Arts, especially since this year's conference coincides with the 85th anniversary of the founding of our academy, which we will celebrate in the beginning of November. Therefore, I would like to begin my address with a brief presentation of the Slovenian Academy of Sciences and Arts. It was established in 1938, but it was by no means the first academy on Slovenian territory. This was the Academia Operosorum, the Academy of the Diligent. Inspired by Italian academies, it was established in 1693 in Ljubljana and would celebrate the 330th anniversary today, but it ceased to work after a few decades. Its members have chosen the words nobis atque alis as their motto. The maxim that work in the field of science should be for the benefit of the domestic, in our case Slovenian community, and for the general good is so timeless and universal that it is also the foundation of the work of the Slovenian Academy. In this sense, we consider ourselves as a successor of the Academia Operosorum, although there is no direct link between both of them. The Slovenian Academy is the highest scientific and artistic institution in this country by law, and currently has 96 full and associate members and 85 corresponding members from abroad, working in 6 sections. Slovenian Academy also nominates external experts to different academy working bodies, such as the Council for Energetics, Council for the Protection of Environment, and the Council for Development, which was recently established as a platform for a broader expert discussions on issues related to Slovenia's long-term development. Otherwise, the Academy's main tasks include addressing fundamental issues in science and arts, participating in the formation of research policy and artistic creation, developing international cooperation in the fields of science and arts, providing science-based advice to political decision makers, and last but not least, promoting science and arts. To this end, we organize various conferences, symposia, roundtables, lectures, and debates on national and international level. To illustrate, in September alone, we organized a panel on the introduction of artificial intelligence to Slovenian schools, which addressed a very relevant topic, a symposium on lexicography as a part of our ongoing care for the Slovenian language, to which we devote a great deal of attention. Further, an international colloquium on art in Slovenia between the periphery and the center in the early modern period. And finally, a lecture on basic molecular biology. I should also mention the Academy publishing activities and international cooperation, which are also an important part of our activities. In addition to the Academy yearbook, containing annual reports on Academy activities, we also publish serial publications of individual sections, symposia and conference proceedings, periodical publications, among which also with regard to today's conference, I would like to highlight the internationally highly profiled journal Acta Carciologica, as well as extra serial publication of Academy members. The Slovenian Academy of Sciences and Arts currently has in place 45 bilateral agreements of scientific cooperation, mostly with the European academies. It is also a member of a number of academies association. We cooperate more extensively, mainly with Central European academies and with the academies in the former Yugoslav republics. It is a particular pleasure for me to mention here our excellent cooperation with the European Academy of Sciences and Arts, with which we have also organized today's conference on the subject of water. Ladies and gentlemen, water is a word most closely linked to life. It is one of our planet's most important and absolutely indispensable goods. It is therefore not surprising that humankind has always paid great attention to it. Today, in a time of increasingly acute climate changes, growing pollution, and poisoning of our environment, this is an even more urgent task. Today's conference is therefore just one of many that are in one way or another related to water, which in our case has also a specific symbolic meaning. Since it is water, I'm referring here to the Danube that binds our academies. One of the many changes we are facing in the protection of the environment and preservation of natural water resources is the protection of the environment and preservation of natural water resources. Climate changes, pollution, and inadequate management of water sources affect water-dependent ecosystems, as well as our health and well-being. Access to safe and clean drinking water is still not assured for all, and the outlook for the future is not optimistic. This is a great challenge we face. Flood risk is another pressing challenge. This August, Slovenia has experienced firsthand the scope of damage flooding may cause. It is measured in billions of euros, with restoration work likely to last for years. And the consequences, such as diverting money from investments to reconstruction, will be felt by society as a whole, not just by those directly affected by the floods. As a source of energy, water is also an important place in the context of reducing the use of fossil fuels, lowering carbon dioxide emissions, and the transition to a carbon-free society. Unlike wind and solar energy, water is a constant and a stable source of electricity. This is its great advantage, although its use has, of course, many limitations. Science has a crucial role to play in addressing these problems and challenges, which can only be successfully solved through a scientific approach. This is where today's conference wishes to contribute, and I wish it every success. Finally, I have only the pleasant duty to thank Professor Branko Stanovnik, head of our Department of International Relations and Scientific Collaboration, for the successful organization of today's conference. I would also like to thank all those who helped in its preparation and wish all our guests a pleasant stay in Ljubljana. Thank you very much.
Thank you very much, Professor. And now I would like to invite Professor Klaus Mainzer to give opening address on behalf of European Academy of Science and Arts. And Professor Mainzer, the floor is yours.
Dear members of the Danube Academies, ladies and gentlemen, it is also for me a great pleasure to open this year's Danube Conference. As President of the European Academy of Sciences and Arts, I bring the greetings of the entire Academy. As you know, the Danube Conferences are closely linked to the ideals of the European Academy of Sciences and Arts, to use the diversity of European countries and cultures for common developments in science and arts. What could be more obvious than the use of the Danube River as a unifying natural bond to link the various national academies located on this great European river to jointly moving thematic conferences? I would like to take the opportunity to thank the Slovenian Academy of Sciences and Arts, always in these beautiful buildings here in your capital, and I saw your office. I was very impressed. Our office in Salzburg is much more modest, and especially you, the president of the Slovenian Academy of Sciences and Arts, for hosting this year's Danube Conference. This year, the Slovenian Academy of Sciences and Arts, together with our European Academy, has focused on the theme of water. During this presidency of the European Academy of Science and Arts, the topic of water has already been dealt with in detail in an Academy expert group on climate, environment and energy, and considered in an Academy position paper, which was also recently published in our new Academy's journal. The technical, ecological and economic potentials of hydropower are obvious. Next to fire, hydropower is one of mankind's oldest form of energy, which has been used in Europe in particular since time immemorial. Since the beginning of the 20th century, hydropower generation has been considered reliable, controllable, and storable. And since the end of the last century, at the latest, however, ecological considerations have also come to the fore. The use of hydropower can damage ecosystems in the short and long term. In the past, effectiveness and maximization of hydropower in large hydropower plants were considered exclusively desirable. The dammed areas set up for this purpose can have a positive impact on the landscape and be used, for example, as recreational areas near urban centers. On the other hand, the establishment of such hydropower plants can also severely disrupt nature conservation and biodiversity. In the sense of complex systems dynamics, and personally I was engaged in this research on complex systems and nonlinear dynamics since decades. Complex systems not only in the natural sciences, but also in economics and in the social sciences. In the sense of complex systems dynamics, global ecological effects can thus be triggered by such local measures. Therefore, hydropower has to be carefully assessed, taking into account, for example, river ecology, nature conservation, biodiversity, and social use. Last but not least, from a mathematical point of view of modeling, the non-linear feedbacks of these factors must be kept in mind. Non-linear, by the way, is a mathematical term. It roots back to the equations which are used to describe these complex feedback loops. And describing them with nonlinear equation means practically that they are very difficult to handle. Mostly from mathematical point of view, there are only approximations. Now, nonlinear interactions can trigger conflicts of objectives for renewable energies. Hydropower is undoubtedly renewable and therefore an important part of the overall European strategy for energy use. However, there is also the intrinsic value of water landscapes from an ecological and cultural point of view. On the one hand, there is the European requirement to significantly reduce greenhouse gas emissions by 2050 and to do so by 2030. Renewable energies such as hydropower should contribute to this climate target. On the other hand, the protection goal of ecosystems must be taken into account, which must be able to recover even after intervention. The corresponding complex natural system must therefore be resilient. That is another keyword in this complex systems approach, must be resilient in the sense of complex systems dynamics. At the European level, the requirements of nature conservation and water ecology have been significantly strengthened in recent years. Innovations in hydropower technology must be designed according to the imperatives of ecological sustainability. Practical recommendations for planners, authorities in politics, and operators are to be developed and implemented on the basis of scientific findings. Ecosystems of water are subject to complex system dynamics, the stability of which is a considerable challenge under the utilization pressure of renewable energies. Existing infrastructures for the use of hydropower should therefore continue to be used from an ecological point of view. One example is the environmentally compatible expansion of existing large hydropower plants. However, the supposedly climate-friendly energy aspect of hydropower should be put on the back burner, where water landscapes need to be safeguarded for future generations in terms of sustainability. In an overall portfolio for Europe, the advantages and disadvantages of, for example, solar and wind energy, hydropower, hydrogen, nuclear, and fusion energy must be weighted against each other and combined in the end in a hybrid energy system for Europe. In this sense, water must also be oriented towards a sustainable future in an overall European portfolio of energy technologies. In this portfolio, diversity must ensure resilient behavior in order to be able to react flexibly to the risks of the future and to recover overall in the event of selective setbacks. And in that sense, I wish the conference exciting presentations and fruitful discussions that will have an impact on our academies along the Danube River. I thank you for your attention.
So thank you, Professor Mainzer, for your opening address. And now I would like to say just a few words about the conference. This conference is divided in two parts. Today is scientific part in which 13 communications will be presented, 12 of them orally and one of them as a video conference. From 6 different countries, these are Slovenia, Slovakia, Serbia, Montenegro, Belarus, and tomorrow there will be an excursion to Karst Research Institute of Scientific Research Center of Slovenian Academy of Sciences and Arts and to Postojna Caves. And now we shall proceed with the first lecture, which will be given by Professor Martin Grambo of Bavarian State Ministry for the Environment and Consumer Protection, and also from Technical University of Munich. He will talk about impact of anthropogenic land use on the regional water balance. Professor Grambo, the floor is yours.
Yeah, good morning, Excellencies, Presidencies of the Academies. It's a big pleasure for me to speak here about new ideas, scientific new ideas in the water management. And I think it continues and takes your ideas about complexity. I brought some slides with me. That's the one reason is that it's my poor English, so you can in fact read the things if I'm wrong. But I have to find the presentation. Can someone help me in that screen? Which one is mine? Would be too bad to have
what is
wrong slides. Otherwise, we take it from the stick.
Okay, I find it.
Ah, wonderful.
Yeah, I think.
Yeah, wonderful. Okay.
Okay.
So yes, it is true. The climate change is beside the wars in the moment the most biggest challenge for every one of us, including the water sector. But if you start when we leave out the wars in the world and go to the climate change as the biggest challenge, we have two ideas to tackle that. The one is that the mitigation is working. Klaus Mainzer told about water power, hydropower as one way to make a better energy resources. But to say it frankly, who in the room thinks that we take the 1.2 degrees aim or even the 2 degrees aim? So in the moment we present new energy, but the energy consumption is increasing. And I don't know if it's our destiny, but we as a water and environment responsibles may not base our ideas on hope. that we can get this 1.5 degree aim. So we have to go in the more and more in the adaptation. That doesn't mean that we stop the mitigation now. Don't understand me wrong. We have to do everything to, first of all, reduce our energy need and then replace by better energy. But we have to go immediately into the adaptation. And we do that if we talking in Europe and worldwide, the people know since years that the water sector will eventually the most critical in this climate change scenario. So when we met in 2008 for the first time, speaking about chances, what could we do against this meta crisis, together with Peter Wilderer, for example, and Paul Crutzen, he was with us. A colleague from the United Nations was with us, and he said the fact is that the good news is that we will not die because of climate change. The bad news is we will die because lack of water. So before we die from climate change, so very very shortly. Yes, and if we try to do something for the water, and this is both. This is flood. Maybe we think this region here maybe is partially a lucky region, because this region is in the 5B stream of these big weather cycles, and eventually you are one of the small regions in Europe and worldwide where the water balance will be increase and not decrease. But it's a hope. You will fight against flood, but let me say, fighting against flood is much easier than fighting against drought. And most of Europe and most of the world will face drought. And drought can ruin whole nations. And drought is ruining whole nations. Outside of Europe, a couple of candidates for this catastrophic development are well known. I don't want to blame some country, but you know the big problems in North Africa, you know the big problems in Iran, in parts of China. But we don't have to go outside of Europe. Look, this terrible story in Spain. They decreased their water level, groundwater level. Meanwhile, in big parts of South Spain, to about 100 meters and more. And unlike the karst we spoke yesterday, it will need generations, 100 years, that this water will come up if they stop the use of that water. And we last week heard that for the first time Spain is starting to send the police and the military to close these unallowed wells. And I say, okay, that's very good, and it's very hard because you're fighting against farmers, against the agriculture sector, and this is typically for politicians the very last thing they want to do. But unfortunately, dear colleagues in science, they are too late. So even if they would stop completely the overuse of the water, they lost these regions. And there is no rain on the horizon. So this is an extreme treat, and we have the same or like the same situation in France. We have the same situation in Italy. Look to the Po region, and it's a source of confrontation. So I've been 1 week ago in Tessin, and they have pretty rough discussion with the colleagues of the Po River, because also there the agriculture is living from the irrigation of the Po River, and they ask for slowing down the lakes, the Swiss Italian lakes. So it's a high conflict zone, and could be part also in the future, as it is typical for the whole world, for interior political problems. So this lack of water is a source of poorness, of people losing their future, getting okay. So it's water is, as everybody knows, a highly political resource, and the more it's not only in the Jordan situation where water is one reason for war. It will be increase, unfortunately, also here. Okay, so we have to do something, the one, Paul Crutzen gave us an idea how to do it, to say it also here in this academic frame. Our problem is, our water management problem is, that many people try to solve, to look for simple solutions. So you have not enough water, drill, make a new well, and take the water from the ground. Nobody is thinking about what is happening with the groundwater. Yeah? Or take it from the river. No one is looking at what happens with the river. So solution, a model for solution is done by Paul Crutzen with this idea of the Anthropocene. I don't have to tell you about this Anthropocene. Everybody knows what Paul Crutzen meant, but we developed the system of the Anthropocene to make it useful for the water management. And this is number one I want to show you, and why it is like that. So mankind did change the face of the world in a way that our impact is more important than any natural impact. Okay, this is the idea of the Anthropocene. We say this is, and is the Anthropocene good or bad? Neither nor. Anthropocene is a description of a situation. And many of the things in the Anthropocene are wonderful, are good, are that exactly what we wanted, but we have side effects, and these side effects are can be dangerous. So, what did we do? We say there are 3 levels of impact of the Anthropocene, and the first level, the regional level, is what we did with the landscape at home in our region. And we if you want, since the Middle Age, we deforest our land because we need farmland to eat. And what we also did, we drainaged the land. Many parts in Europe have been wetland, and wetland is hard to be used. So we drainaged whole Europe in many regions. And last not least, we sealed it with our settlements, our streets and everything. So we completely changed the view of the landscape. And if you see this build on the left, by the way, in the former Austrian Marine Ministry, now the Water Ministry, you see how proud the engineers is showing the irrigation system in the landscapes and the ruining of the wetlands. And meanwhile, in the background of our ecological knowledge and in the background of our drought knowledge, we say, okay, it might be difficult to make this, but this was for 100 years state of the art in many regions in Europe, and because in most regions, especially in the north of the Alps, but you have drainages also in Italy, you have drainages also in Spain, everywhere where we have wetlands, it was drained. Partially for health reasons, we have tiger, mosquito, and something like that, so malaria. But this was what we did because we had plenty of water. And another point is we deforested our land for some reasons, but more we changed the kind of forest. And this is a very interesting graph. That means if you look to the blue line, that's a new built groundwater. It's not translated, sorry, I'd see it in that moment. On the left side, you have grassland. In the middle, you have a natural or open forest. And on the right side, you have a forest plantation. Yeah? And you see that the kind of forest has, in this conservative picture, has a strong impact, and there might be a negative impact of these forest plantations because they use a lot of water and they are all year long green, and they give less water to the groundwater. Let this be open. This will be a core question in the future to understand this right way. But this is an old, more or less old picture. It's not so old. It's 4 years old, but it doesn't understand something new. I will tell you. But the forest play a role in the water management. Typically, it's very funny. We think, yeah, forest is the water castle. Forests make water. The normal people say forests make water. The scientists say forests need water. What is true? And there's something new outside. Okay. And then this typical picture in many parts of Europe, we made our landscape to a farmland, and you see this from Heisenhuber, this development, and most people say, okay, the picture, the first picture, this is a medium age farmland, so this might be too complicated, but the middle picture, the picture in the middle, most people feel comfortable with that picture. And it could be that this landscape with hedges, with small streams, with a different landscape is not only nice for the eyes, but also it plays a role in water management. If this would be true, we have to rethink. So we leave it open here on that point. So these were primary effects. The point is we have these primary effects all over the world, the cultivated world. Yeah? The secondary and mainly discussed effects are especially the climate change. Yeah? The climate change combined with primary local impact. And you know climate change, I don't have to say much about that. Only one point. All the measured points of climate change are in our region worse than the worst case scenario. So whatever it means. But on the other side of this graph, you see an additional point that we calculate the refreshing of the groundwater. And this, in the moment, goes down far beyond the most depressive idea how this will develop. And so we have much less groundwater renewing than we calculated with the worst case scenario. And now the problem, it seems to be a pattern over the northern hemisphere. So the NASA flight the last times and said this phenomenon is not only in Bavaria, it's not only in Germany, it's not only in North Europe. It seems to be in fact all over the world. And what does that mean? The groundwater is feeding our drinking water, but it's feeding the whole nature worldwide. Okay. And this is not the only point. Another secondary effect is the chemical impact. Paul Crutzen, Paul was a chemical, and this was the origin of his idea of the Anthropocene, the impact of chemicals. And these chemicals are working in the same complex ecosystem which is combined. So the worms, all the animals and mushrooms in the ground, which are extremely important for the character of soil, for the water capacity, for the biologic capacity, they are changed more or less by these chemicals. And this again is happening worldwide, and by chemicals coming from Australian coal or wherever they come. The left side, by the way, is something we sometimes we have success. I think this is the fluor chemicals and others. So sometimes if we decide, we can make good things, but reduce the pressure. But unfortunately, the pressure in total is increasing. And to the secondary consequences is what we do with the forest. And this is a screenshot. I ask pictures of dying forest, and these are pictures from all over Europe. And we have in whole regions of Europe, we have dying forests. And if this idea in this October, there was a publish in Nature Water that the forests play an extreme role in the water cycle. This I will explain very briefly. If this is true, then this secondary catastrophe, what happens with our forests, is a catastrophic development. It's a circular vicious. So this happening. And then the tertiary effects, and I might cite Klaus Mainzer. This is working with the complexity. What does it mean here? First of all, we learning old effects by understanding. We understand so little things of this complex ecosystem. It's unbelievable. We not even understand the human medicine completely. There are, and now look to this complex system. So many things we don't understand. We have measurement, and now there's something new. And on the same moment where we try to make something with that system without understanding the system, we change the system with the Anthropocene. So we think we understand something, but the species which is balancing this situation is extincted meanwhile. So we have a moving dynamic system, and I think we have. This is and what happens? It's only one slide. We want to get the good ecological status with the Water Frame Directive, and you know that it's very, very slowly that we get this good status. We should have it in 2027. No way, Europe-wide, no way to get the good status. And this is from a presentation I hold in the EU Commission. They say you have to get it in 2027. What's happening is first of all is that we have much more pressure on the system than we thought, and you see, and that the European Commission in the beginning of the Water Frame Directive estimated 400 to 600 million EQ for whole Europe. This was the Europe of 10 or something like that, to restore the rivers. In Bavaria alone, we invested 710 million. And we estimate that we in Bavaria have to invest 2.4 billion to get the river back in a frame for the Water Frame Directive. And in the same moment, our yearly investment in Bavaria in infrastructure, streets, houses, and everything is 12 billion euro. So in other words, we have to invest much more. Okay, so this is the story about the Anthropocene, and the message is we have to understand the whole system as good as we can, and we have to, I think we have to go back that the system can heal itself. So we transformed these ideas and understanding into our water strategy for 2050. I don't tell about that. If someone is interested, please write me an email. I can give you some papers, or we have another chance. But we try to involve all this knowledge about the combination of biological, physical, chemical system in our strategy, flood and droughts. And now at the end, I think I have 5 minutes more. Is it okay for you? Just a minute. 1 minute. Okay. Then I make it very briefly. We have to understand the water sector itself better, the water balance, and especially the question of precipitation and water vapor. Why doesn't it rain enough? That's a simple question. And it seems that the forests are playing an important role in that equation, but we cannot describe. Only the fog and the so-called horizontal water flow are about 200 millimeter per year estimated. In a frame of 400 or 600 millimeter in drier zones, it would be a quarter to a third what comes by that. And last not least, we have to understand better this interior water. So the landscape is taking the rain, is bringing back the water into the clouds, and this is raining in the neighbor country. First, colleagues tried to calculate that, but we really do not understand enough from that. And you know, in the big frame, the biotic pump, for example, the Amazonas, is the water is transported from the oceans wide into the country. We live from that transported water. And today there was a message that even in the Amazon, this biotic pump stands still. The people say it's climate change. Okay, we cannot do anything, but eventually it's deforestation. If you ruin this system, it's man-made ruining. And if this is true, that the landscape has a serious impact to our water supply, then we have to rethink the landscape. And this was the reason I introduced that in the European Academy, that we're looking for scientists going about this question, because we have to find answers very, very fast. Are we responsible for the changes? And can we do something? Our politicians say, okay, you won't change the whole landscape. Do you know what you're talking about? It's a catastrophe, a political catastrophe. No, it's not. It's a chance. So this was what I like to say here in brief words. Thank you very much.
So I hope that Professor Rambo will be willing to answer the questions, if any. Please.
Can you explain a little bit more about the biotic pump, what you have mentioned at the end?
Yeah, this makes clouds, and then the rain comes. And this is organizing a deep pressure zone which transports additional to the western zone the water from, in that case of Siberian forest, from west to east. In the continental frame, I think meanwhile it is accepted by the science. You know that from the Amazon, UN reported from that. We know that in the Amazon the system is working, and the Chinese in the moment invest billion of yuan in building a biotic pump from the Pacific Ocean into the interior. So in the continental frame, it seems to be accepted by most of the scientists. The very big question is, does it work also in smaller scale? And the experience says yes. If you see the Mediterranean, the deforested islands of Kyklades or whatever, everybody knows that these islands without forest, there's no rain, and there are two islands with forests, it's raining. So from that we would say, okay, everybody knows that this is working, but in the science, it is not really taken as a chance at the moment. And something more, it seems to depend on the kind of trees. So special, effectful seem to be natural forests, not too density, but and with low, middle, and high trees. They seem to be very effective, and this is against our economical forest industry, because they want plant temperatures. So, and this is one reason that it's hard to get data from that, because it would mean a change. Okay. And the same is about the role of the hedges. There are many published data that hedges are very helpful for the landscape. England does it, for example, but in our very intensive agriculture country, the hedges are very often gone away, and this seems to be a catastrophe, by the way, for the streams, because shadow is the new currency. We need shadow for the rivers, otherwise they heat off, and yeah, okay. So this is biotic pump, and I can give you, there was absolutely new, I got it just from Peter Wilder, an article in Water Nature exactly about this biotic pen. I can give you the article, then you can see the origin.
So thank you very much, Professor Gamber. The next will be given by Professor Michael Benčić from the University of Ljubljana, the Faculty of Natural Sciences and Engineering. And he will speak about water resources in Slovenia. Professor Benčić, the floor is yours.
Okay, thank you. Thank you for giving me the opportunity to talk about the water resources in Slovenia. My talk will be not so strategic as was the former one, but for sure I will tackle some questions because they are pertinent for all of us. And I will try to illustrate the conditions here in our small country, how and what kind of water we have, where this water is, and on the other side, what are the conditions, or maybe also some future prospects. Of course, it is impossible to explain everything in this short lecture, but I will try to do my best. From professional point of view, I'm hydrogeologist dealing with the groundwater. I have experience, let's say, from the industry. I worked for 20 years, nearly 20 years for geological survey. They are worked for water supply problems and everything what is related. And nowadays I'm in academia teaching hydrogeology at the University of Ljubljana. So I will try to explain a little bit about the starting points of the water in Slovenia. Then I will talk about the meteorological conditions. Of course, then we will tackle hydrology. And then at the end, I will try to explain very briefly something about the water management and the governance. And of course, as every lecture should have at the end, our conclusions. So Slovenia is the country positioned in the area where several geographical factors are favoring the conditions of water abundance. We are considering ourselves as a water-rich country. And this is the consequence of meteorological conditions on one hand side. On the other hand, this is geological situation in the country and, of course, physical geography. And we have a perception in Slovenia, especially plain people, that water is everywhere, that we have a lot of water, but it is not so simple. We recently, since 2020, experienced several hazards related to the climate. And this is consequence somehow of the climate change and related phenomena. But nevertheless, we have a positive national water balance. And as a natural scientist, we can consider water as a natural phenomena. But as it was already explained, water is not just a natural phenomena, it's also socio-economical phenomena. And we know very well that water is related to the economy, water is related to the standard, and this is very much depending how the society is functioning. So this is not the case that international organizations are interested in water issues. And nowadays, Slovenia, I must say, put a lot of efforts and energy to be part of these international events related to water. Just recently, we have a presidency of so-called Water Convention in Geneva. So, as a society, we understand that water is important. But of course, as every society, we have a lot of open problems and questions related to this. So, this is statistics from the World Bank. And as we always say, oh, Slovenia is very, very rich with water. But when we list how much water we have, of course, we are about the average, but we are not so good that we will be at the top 10 of the world. Here is the list from the World Bank Open Database. But of course, if we compare ourselves to European conditions, we have, let's say, good position in the national water balance. So there are data that we are 6th in the European Union or the European continent at the 10th. So let's have a look to the natural conditions. As I said before, it is very crucial that we have somehow special geographical conditions. And this is a relief of our country. And what you can see, we have two big mountain chains which profoundly influence the meteorological conditions. First is Dinaric Ridge or Dinaric Mountains in the southwestern part, and then we have Eastern Alps in the northern part, you can see from the relief. So this is one precondition which is also important for the water abundance here in our state. This is the distribution of the temperatures. It is also important for water distribution. Why? Because it influences water cycle. And the influence of temperature on water cycle, we can see, we can feel it. Because if we have higher water temperatures in the air, it means that we have higher water cycling, we have higher evapotranspiration or transpiration, evaporation, and so on and so on. But temperatures are, due to relief, not so high. Then, this is very crucial to understand the distribution of water. This is the distribution of rainfall in the country. And what is interesting, Slovenia is relatively small, but we have a really large precipitation gradient. We have, for instance, in north, northwestern part, where we have mountains, even more than 4,000 millimeters per year. So it means 4 meters of water. And then if we go to the east, to the northeastern part, you will find out that in the far east, it's nearly 850 millimeters. So it means that we have the difference 5 times in the precipitation. And so these big gradients in precipitation are, on the one side, of course, the consequence of the meteorological conditions, mixing of so-called Geneva anticyclone and the cyclones from the north. But at the same time, it is the result of the orographical barrier. And these orographical barriers are positioned here in north western part and south western parts. And this is also another very interesting thing. For instance, when we are talking about rainfall, it's also important what kind of intensities are. And these intensities are very much influencing the development in space, and how we already heard a lot about the landscape use, how the landscape is equilibrated to these precipitation conditions. And what we can see, we have here, it's just one derivative from the return periods calculation, but it is interesting. You can see on the northwestern part, we can have, with the return period of 100 years, more than 450 millimeters per day. This 450 millimeters per day for some countries is the average precipitation amount on the annual basis. So it means that in parallel to relatively high high precipitation, we have also very intensive rainfalls. And this is also important how the infrastructure is later developed according to these conditions. And these intensities are also very high in the other part of the country, not just in the mountainous region. And at the end, I will touch a little bit our floods from the August, and you will see that these floods were very much related to this intensive rainfall, which is possible here. It's also important to know what is the evapotranspiration. For those who are not hydrologists, the evapotranspiration is simply what is returned back to the air with the evaporation from the bare ground and also from the forest. And we already heard a lot about the forest, and forests really profoundly influence the hydrological balance. Probably we will hear more about forest also later on in the lecture of Dr. Rauber. And this is the network of rivers and creeks in Slovenia. And what you can see that in some parts this density is, the density of creeks is very high. But there are regions where no surface water is present. And this is also very crucial to understand the water resources in Slovenia, because as a country, and we probably know, we have a lot of karstic aquifers, and the share of the karstic aquifers is a little bit below 50%. And you can see that relation between surface water and how surface water develop is very much related, as I will later show you about geology. And this is hydrogeological map of Slovenia. And what you can see, everything is green for the first impression, of course. And what is this green? This is karst. These are karstic aquifers. So from this illustration, you can see that nearly half of the country is covered by green color. And then we have also some blue color. And this blue color is also important for understanding of water resources in Slovenia, because it is also related to the larger cities which we have. And the main supply, water supply, is coming from these blue colors. And what are these blue colors? These blue colors are so-called alluvial fans. So it means gravel, sand, and something like that. Then it's also important, we already heard about the dams, the retention of water, and so on, and how crucial it is. And so for the country and for the national water balance, it's also important how much of water we retain. And this is very much related to what we call runoff. And this runoff consists of two parts. One part flows on the surface, and another part flows into the underground by the infiltration. And so we are putting a lot of efforts to understand how these components are related. And of course, these components are related, of course, to the input, which is related to the precipitation. And on the other side, it is related to geological, or we can say hydrogeological conditions. And so here we see the total runoff. And of course, the total runoff is the highest, again, on the northwestern part, where we have the highest mountains. But what is interesting, that when we look to the rest of the country, we can see that there is not much diversity in this runoff, that it is more or less nearly very similar or the same on the total scale. So let's look now to the surface runoff. So this is water which flows on the surface. So we can see again that there is not so much diversity, but it is related again to the relief. So what is the altitude, how the relief is formed, and so on. But now I will show you the infiltration map. And this is the parameter which shows us how much water goes into the underground. And what you can see, that this map is much more diverse, and it is also interesting that blue color is much more spreaded like in maps before. So it means that we have really high infiltration to groundwater, and this is also very important for our water balance at the national scale and of course of development. There is a national water balance. I will not go to in details, but this is from our Agency for the Environment, and you can see the shares of how much precipitation is transferred to these components I already explained. So nearly 45% of water goes back to the air. Then we have 55% of the runoff, so water which flows out. But the share is also interesting concerning surface runoff and underground water, and you can see that underground water, literally speaking, used 20% of the precipitation. And this is again very high share if we compare this with some other places around the world. And very often I'm using this comparison, how much Olympic pools per person we have in the country. It's a populistic comparison, but it is very nicely used for the plain people because they don't understand what is cubic meter per second or cubic meters per year or something like that. And you can see that we have 6 Olympic pools of rainfall per person in the country. This is really very large amount of water. So you can imagine how much water is this. There are some numbers for those of you who maybe knows this better. We have, as I said, relatively high outflow. So we have 550 nearly cubic meters per second is flowing every second from the country. This is a really large amount. And then we have also high amount of the groundwater flow, high amount of surface water flow. And now we are coming for one very interesting thing. I don't know if you know, even some Slovenians don't know this fact, that in Slovenia nearly 95% of water is coming from groundwater. This is very special. This is really a very high amount. And why? Because we have so good hydrogeological conditions in the country. Groundwater is nearly everywhere. And what is also important is that this groundwater is coming from usually carbonate rocks or carbonatic sediments, what this means that water is good for tasting also. And that's also one of the reasons why we are using this groundwater. And we can see how much water we are using per capita per day for everyday's use. And it's also very interesting that there is, how to say, everybody is believing that we are using more and more water each year, but it's not true. In Slovenia is the case that this number is relatively constant from year to year. And there are several reasons for this. And what is also very good for us is that we are using really a very small share of this groundwater. So we still have a lot of space to use this groundwater for some other purposes, but of course we have to be very careful with this. I will tackle just very briefly, I can talk about these hours about management and water issues and the governance, but Slovenia is very much related from the legal point to the water business and water issues to the so-called European legislation we are using as a baseline, so-called Water Framework Directive. But in spite of that, we have very complex legislation. You have to be really specialist for some parts to deal with it. And what is interesting is that we have, how to say, very special relation to water. And we can talk today about hydrosocial cycle. And this hydrosocial cycle literally means how water flows through the society. And this flow of water through the society is really very complex. I believe that also in other countries you have many experiences with this. And this complexity of water cycle through the society is reflected in Slovenia in some very interesting event. In 2001 we have water referendum. I will not go in details and political sides and so on, but what I want to say is that this water referendum, which was really very high accepted, it changed the perception of water here. So it means after this referendum, nevertheless, on which side you are of the referendum, you can see that we really changed the perception and relation to water as a society. Then I would like to tackle also the problem of drinking water protection zones. As I said before, we have 95% of water coming to the waterworks from the groundwater. So consequently, it means that we have a lot of country covered by drinking water protection zones. According to some statistics, this is 15% of the area covered by the water protection zones. Unfortunately, I have only black and white, but you can see these patches. These patches are protection zones. And these protection zones are something which is very complex. So for us hydrogeologists who are dealing with these protection zones, we have several approaches, methodologies, but to be short, it's different for karst and it's different for other areas. And you can imagine that when you have such zone, this zone is intended to protect the water resource. And because they are covering a lot of place and space, there are a lot of conflicts. So usually we have a protection of water. On the other side, we have other interests for developing of space, developing of agriculture, and so on and so on. And so recently, we have a lot of conflicts related to this, especially in Ljubljana. We have one problem, then we have some problems in Styria, and so on. And I will not go to details, but we should and we would change the relation to this water supply, because we are more or less in Slovenia, maybe you don't know, but in Ljubljana you can open the tap and this water is not treated. It goes directly from the aquifer to the water works. So we should work in this direction to sustain this good quality of water. And so we have to rethink also the problem to the protection of water. I will very shortly, I will be short now. In this year, we experienced severe floods, especially in central Slovenia. We have, as it estimated at the moment, 15% of natural gross domestic product is related to the damage, probably. And so we have really this challenging event. And this challenging event, it's also related to the how we are tackling with the climate change, the changing in the climate related to the water cycle. Because temperatures are rising, it means that the water cycle is coming faster and faster. And as I said before, we experienced already several hazards related to climate. And last year we have really severe drought. So on the one side, we have severe floods, and the other side, we have severe droughts. And this is something we should tackle and challenge in the future. And as I said, there are many social hydrological challenges for us, and I believe that these challenges are very similar to your countries. Thank you very much.
Thank you very much, Professor Brenčić, for your very interesting talk. And the question is open, the lecture is open for questions. If not, then I would like to thank you once again. Thank you very much. And the next speaker is Professor from KAST Research Institute of Scientific Research Center of Slovenian Academy Sciences and Arts. And here we speak about the evolution and characteristics of karst aquifers.
Okay. Yeah, I will speak about the karst aquifers. So let me first go what karst is. Karst is, of course, landscape on soluble rocks. In moderate climate, we more or less relate karst to carbonates, which are limestone and dolomite. But of course, you can have karst features also in salt, in gypsum, and so on. But in moderate climate, salt and gypsum are quite easily dissolved from the surface, so we don't see it. But if you leave landscape long enough, like, I don't know, a couple of 100 million years uninterrupted and just subjected to water, then karst features also evolve in non-carbonates or also in silicates, for example, like in quartzite, shown down here. Well, if there's about 15% of the ice-free land, of the Earth's ice-free land, which is composed, which is underlain by karst rocks. So it's an important system. And there's about 20% in Europe and, well, just almost 50% in Slovenia. So these features, these landscapes are really important. And we have to say, as Micha also already mentioned, that this is also about the portion of people which are supplied from the karst aquifers. In Slovenia, even more. So I'll just leave you first with a few nice pictures of how karst looks like. It's of course beautiful, attracting curious people. I will not show too many pictures of karst. It's also characterized by strong springs. This is, for example, Polje in Slovenia. Caves are, of course, as characteristic features of karst underground. And I have no time to leave you enjoying in these pictures, so I have to go on. Yeah, so this is somehow, a conceptual picture of it. Of course, karst is preconditioned by geology, climate, if you want, hydrology. But once these conditions are set, and these conditions are also changing in time, there is an important difference from the other landscape, because the flow through the karst system is, of course, also brings also the solution and formation of conjugate system within the karst massif. That means that we don't have just a simple porosity which is being made from the origin of rock, but the internal structure of the karst is continuously changing because we have evolution of conjugate systems. And everything is, of course, interconnected in a complex feedback loops, as Professor Mainz already mentioned before. Understanding these feedback loops and formation of how these massive turn from something which is initial to something what we observe is, of course, challenging. Typical, if you take just the karst aquifer, typical or a characteristic for karst aquifer is that they are extremely heterogeneous. Let's say the scale of hydraulic conductivity spans 10 orders of magnitude, because we have, intergranular porosity, we have fracture porosity, and in the end we have conduit porosity, we have caves in there, which of course transmit a large amount of water and sediment, if you want, and they completely change the behavior of the system. So in karst, it's also important how the water is being infiltrated. Water can enter karst through large streams, sinking streams. If the karst area is next to a non-karstic fluvial area, these rivers can enter karst in a concentrated way. The water can be, and can enter karst areas dispersed. You can have, also the small basin within the karst systems, and all this water kind of is then drained by the conduit systems. And of course, the conduit system interacts by surrounding fracture system, and this is drained to springs. And characteristic for karst is also that we have very abundant springs. In no other regions you would have springs which can bring several hundred cubic meters of water per second in high water. So let's look a little bit at one of these, how these systems form. I will show few modeling attempts, because models help us understanding why karst systems are like they are. And of course what we are asking is, well, we have a block of limestone which somehow goes out from the sea, and then it's subjected to the water cycle. You have a ground water flow through the massive, and of course because this flow dissolves the fractures along which it flows through, you have formation of conduits, and we ask ourselves how these conduits form. Well, it's in a way we need several ingredients. If we want to understand that, we need chemistry, and of course this is an overall equation saying what's mostly happening in karst. So we have a water CO2 calcium carbonate system, and important role is actually the CO2, which increases solubilities for almost an order of magnitude compared to so if we go to a typical karst spring and measure what is the amount of dissolved limestone in there, you would measure like something like 200 milligrams per liter. If you would take a distilled water, you would get like 10 milligrams per liter or something like that. So it's a big importance of CO2, and the CO2 in karst has very many implications and many consequences that I don't have time now to talk about them. So each droplet of water in karst can either be, can be undersaturated with respect to calcite, it can dissolve calcite, it can also be supersaturated with respect to karst, to calcite, so it would precipitate calcite. That's why we have all those, flowstone forms in caves and things like this. It's not only important how much the water can dissolve, it's also important how fast it dissolves, because we need dissolution rate if we want to study how caves form. And of course there are several processes which define what the solution or widening rate, if you want, can be under certain conditions, but generally the closer to equilibrium the solution is, the slower the dissolution rate. So let's have just a short look into, into how these conduits form. And let's start just with a series of fractures which can evolve from by draining the water from, let's say, a higher position to a lower position lake, like shown in this case. So what we have to do is, if we want to model this, like with computer or analytical models, we have to couple flow, we have to couple dissolution, and we have to couple transport. And, this is a simple setting. This setting transformed into an even simpler setting, assuming we have a uniform fracture. What we can expect is that, of course, because of dissolution, the concentration of solutes will rise along the fracture, and the dissolution or widening rate will drop. But nevertheless, even if when this happens, there is a little bit of opening along the time, and this a little bit of opening brings in even more flow into the fracture, which brings in higher dissolution, higher widening rate, so we have a feedback mechanism. Higher flow, higher dissolution rate, and it goes back to the increasing of flow. So if we look how such fracture would develop, it would develop, you know, very slowly and initially. This is a logarithmic scale. Very slowly initially, but then after a certain time, we call it a breakthrough time, it would develop in a there would be a increase of flow rate, dissolution rate for several orders of magnitude. We can, of course, say, yeah, karst is not a single fracture, it's a complex network of fractures. So we can extend the model to assume that we have, you know, like a two-dimensional network of fractures and pushing the water from one side inside and leaving outputs on the other side and see what happens. I will not go into detail, but the things start to become more complex. Of course, this picture shows how wide the fractures are. The color tells us how fast they are evolving at certain time step, and this shows us the flow distribution. What happens is that you have several pathways which compete to connect input to output. But one is a little bit more successful, and that one suppresses the others. It's like a social environment, you know, the more successful in the beginning tend to suppress the others. But once this one succeeds and breaks through, then the others can start to grow, and we have bypassing, we have integrating the network, and in the end, if we would have really a large amount of flow or large amount of water available, we would end up that we have some kind of a labyrinth maze-like system, so everything would be populated. But it's typically we don't have enough flow. So this is, for example, just, you know, going from the models to reality, because in a way, you know, we have to somehow say that the models really are mimicking what's happening in nature. So this is just an example of ice, of a glacier, and in contact with limestone and caves which have formed along the boundary with the glacier. And in a way, we use these models to interpret such situation in Norway, for example. We can also use these models to study the transport properties of karst aquifers. So we can take a model at certain stage of evolution and just leave, I don't know, particles, in this case particles, or any kind of solute which is entered, and then just study how these particles spread through the system. And this helps us understanding, you know, the things we are observing in nature. It's not mimicking the nature, it just helps us understand some feedbacks which are present there. A general formation in karst which we often observe is like, you know, we don't have infinite amount of water, but we have, like, I would say, we might have some kind of a discrete inputs with limited reach, with limited amount which enter the karst system. And in this case, what happens is that we have some kind of a back-propagating system. So we, in a way, end up with a branch work going from the river into the massive, and this branch work in the end ends up with some selection mechanism that I have no time to describe. It ends up into bringing this water to a small number of springs. So that's why it's kind of inherent behavior that the karst develops, so that the water is actually brought to large springs. This is, let's say, a conceptual view of what I was just saying. So you have, like, you know, this is a cross-section, a backward propagating system. So we have initially there is no karst developed, but of course, first the one closest to the output develops, closest to the erosional base develops, because this one has gradient to growth, and then once this one develops, then it allows the others to develop as well. So in a way, we have some kind of a back propagation, which showed this by modeling, and it's also observable in many karst systems in the world. What we often have also in karst is that we do have cave levels at particular elevations. So we do have a distinct cave levels. So the question is how these cave levels, for example, develop. One of the answers might be something like this. So imagine you have, karst will always try to adapt to an erosional base, to where the rivers are. So it will develop, and if you leave the river at the same position for a long time, you sooner or later would build something which is called water table cave, a large cave system which goes directly to a river. But if you have like downcutting of the valley or uplifting in tectonic settings, then of course karst will, the channels will try to follow this downcutting. So you might have the formation of a canyon. On the other hand, what can happen is that because you have this downcutting, new pathways develop further down, and they may capture the entire available water, and this upper channel remains standing in the air somehow. I don't know, 5 minutes, yes. So instead of just theorizing, I will go now to a real cave system, to a real karst system. Of course, we can observe karst. We observe the groundwater karst. Typically, we observe it at springs. But more and more, since we have new instruments available, we can go down the caves and really place the instruments which are autonomous in the caves, and then retrieve the data and see what's happening. And typically, we have an access to the so-called epiphreatic zone. This is this darker blue zone, which is the level where you have fluctuations of groundwater level. And I will just present, some results from one set of such observations. Particularly in areas like here, in the young orogens, like Dinary karst, or in alpine areas, karst is not only developing by itself due to the solution and things like this, but there is a continuous change of boundary conditions because of tectonics. There's a continuous change of structure. So in the end, what happens is, if you would have undisturbed block and just leave it karstifying, sooner or later, the channels will be big enough to accommodate all the water available. But because we have a continuous disturbance of these blocks due to tectonics, breakdown, and so on, so we have restrictions to flow. And these restrictions to flow cause large fluctuations in the underground. So this is an example of Kras Plateau, Kras karst, so it's a bordering limestone plateau between Italy and Slovenia. It's encircled by non-karstic flysch area, and the main line which we'll talk about is, which I will just shortly present, is this line of the underground flow of Reka River between caves of Skotjan and springs of Timao at the Trieste Bay. So these are some spectacular, so this is completely different from what we can model. This is what we observe, some spectacular pictures of caves where we have this underground flow. In cross-section, which is much more clearly shown, it looks like this. So we have flysch where the Reka River comes. Reka River has really high discharge fluctuation. It goes practically from zero. There's no water coming to underground up to 350 cubic meters per second. And of course, because we have these restrictions, we have large groundwater fluctuations. And these groundwater fluctuations reach more than 100 meters. So at the flood, the water can rise for 100 meters in several hours. So these are, for example, the results from different caves showing what happens in one of those big floods. So this is Scotian Caves, very famous, of course, UNESCO heritage. These are the astronauts which were trained in the area in the Scotian Caves, somewhere here in the middle. This is somewhere here at the end, and this is Scotian caves at floods. So practically entire cave, 90 meters, it's flooded by. And what happened is, by carefully looking at the data in Scotian caves and in the other cave which follows it, we realized what somehow causes the flood in Scotian caves. Because what we thought before was that simply that there is a large cross-section change at the end of the cave. Here we have a cross-section something like 100 meters high, 50 meters wide, and so on. And it goes down to more or less 20 square meters. But it came out that it was not that this was the cause for the flooding, but it came out that in the cave which follows it, the constriction in that cave causes the flood. So we even, tried to model it with hydraulic models, and in the end we end up with results which very closely resembled what it was observed. So the structure of karst underground is really hard to foresee, to know. We are using different geophysical techniques to do it. One recent technique which is probably to some extent promising is the use of continuous time-lapse gravimetry. For example, in Scotian caves, we were able to actually detect floods and even, get the shape of the flood solely by installing the gravimeter, which was continuously measuring the gravitational field, and then by, of course, filtering off all the other effects, we end up with hydraulic effect, and this was, the result was okay. And there's still a lot of challenges in karst. This is just the last picture, just showing vadose flow. The transport through the vadose zone is really hard to tackle because it's not connected. There's, it's gravitational flow. And this is just an example of a dye tracing which my colleague did maybe 20 years ago. So it's like 70, 80 meters thickness. And she flushed the dye with 6 cubic meters of water and followed the trickles down here in the cave. And the first appearance was like from 75 minutes to 95 days, depending on which trickle was sampled. And she could detect uranium at some of the trickles for 2 years. So that, I think, poses a big challenge to understanding karst and to protecting it. This huge span of time that particular pollutant can stay within the system. Because we often consider karst as something, you put it in, it's flushed through the springs, but it's not. It can remain for years before it might be, activated by transport. Thank you.
Thank you very much, Professor. Thank you for your exposition. And the lecture is now open for questions. Please, Professor Hansen.
Thank you very much for this very interesting talk, because it nicely illustrates the foundations and the use of nonlinear system dynamics, which I already mentioned. I have two questions.
Yes.
One is more technical, the other one is more political.
Yeah.
The technical question, you underlines the complexity of these karst networks, and the point especially that the constraints of the networks are permanently changing. And that is, of course, challenging for modeling, because you are interested in certain control parameters in order drives the phase transitions
Yes.
to other scenarios.
Yes.
So question is, how do you handle this changing of the constraints and conditions of the model technically? The other one is more political, namely, I think these networks and dynamical modeling is, of course, important tool for early warning systems. And so the question is, how much is that used, for example, by politics in your country for further shaping landscape and things like that? Because we all know from the climate model, if there are certain critical values, then this is the red line. Then we have no chance to intervene or to control. And therefore these early warning systems are very important, even from a point of view of policy.
Yeah. So the first question, how do we take into account the changing of, internal structure or whatever into these models? It's simply, we assume it, so we are changing continuously. We are playing what happens if you change the boundary conditions, if you change the structure, how the system will evolve. But I must really stress that at this point, these models are still primitive enough that we can just, use them to help us understanding what we observe. We don't use them for forecasts, but of course, if one would have a huge computational power and, then run with, hundreds of models of higher complexity than it was shown here, then I think that at some point in the future we can actually really use them somehow to predict. But in the end, I have to stress that, for example, an important municipal water supply for the central part of Slovenia is completely controlled by one breakdown which happened I don't know when ago, but it's completely controlled by there. So if there is a breakdown in the cave somewhere, it can change the regional flow. You can lose water at some springs and you might get new springs. So it's really tricky. And how to use this in politics? I mean, first we have to somehow. This is a question I don't know how to answer. But for example, I don't see these particular model, like generic model, the model which simulate the evolution of cars. I don't see them really. Not immediate, but in a let's say in a reasonable time, potential to have to incorporate it into the early warning system. But we have to use the knowledge we get from these models to build models which are based, let's say, on observations, and use those models in order to predict what would happen and things like this. So I don't know if I answered you. Yeah.
So thank you very much. Again, the next speaker is Dr. Natasha Rauber from KASP Research Institute of Scientific Research Center of Slovenian Academy of Science and Arts, and she will speak about is the recharge of karst aquifers influenced by large-scale forest disturbances. The floor is yours.
Dear distinguished guests, dear ladies and gentlemen, dear chairman, thank you very much, and thank you for the invitation. My name is Natasha Rauber, and I come from the Karst Research Institute. It is an honor for me to stand here and to present the collaborative work of the colleagues from the Forestry Institute and the colleagues from the Karst Research Institute. In the project called For Karst, we joined forces of forestry and karstology knowledge, And I also thank the previous speakers, especially Professor Brincic and Professor Gabrušek, to present the background of my talk, so that then I can now go straightly to the point. This is the wind throw. It occurs every year in several places. Especially this year, we in Slovenia had several cases of wind throws, also in karst regions. Now, this is the ice storm in the forests in 2014. In Slovenia, it occurred and it damaged about half of the forestry land. And this is the wildfire that occurred last year in the Kras region, which was especially hit us very much because the Kras region is somehow, we call it classical terrain for the phenomena. There, almost 40 cubic square kilometers was completely or partly burned. But these pictures could also be elsewhere in Europe, from Greece, from Iberian Peninsula, from the United States, and also Professor Brincic mentioned drought that hit us last year. So these large-scale forest disturbances are occurring, maybe also more frequently than in the past years, in the past decades, and also they are becoming larger and larger. And there are also some other large-scale forest disturbances like pest and diseases outbreaks, wind throws, and so on, that could have very severe consequences for the vegetation. And what has this got to do with karst? You've seen similar map before. This one is showing in pink color the karst areas around the world. About 15% of the land surface is covered by karst, we have heard. And the green patches are showing the forested karst landscapes. So 1/3 of karst is forested, and you can see that the forest on karst occurs in different geographical areas, in different climate conditions, so it is worldwide important, we can say. And now let's zoom into Europe. Also here, about 1/5 of the land surface is covered by karst, and more than 1/3 of it is forested. Almost in the middle of the picture is Ljubljana situated, and you can see that we are almost in the middle of a very wide forested karst area that you will also experience tomorrow. Beside the very rich biomass, forested karst aquifers also host very rich and very unique biodiversity, also some endemic species, like in the picture below, it's a Proteus anguinus, endemic animal from caves in the Dinaric karst. So there is very high floristic and ecological importance of karst aquifers. And there, we also heard today, important as freshwater and as regional water sources. That is why we were interested, what could large-scale forest disturbances mean for karst aquifers? If they pose any difference to the recharge, the way the karst aquifers are recharged, and also if there is some influence on the springs. And of course, what did we do? We first digged ourselves into the literature, into the information that is available. We also made quite a thorough review of the articles published, and we saw that papers that are dealing with the vegetation change is quite abundant, and we found about 160 papers, and 1/3 of it was done on karst areas. However, about 1/5 of these papers were dealing with the natural large-scale forest disturbances, while majority of others were dealing with forest management or land use changes in general, and so on. Furthermore, most of these studies were done on the plot level. There were very little studies done on the catchment scale. And also, most of them were dealing with the evapotranspiration processes. The studies were done in the scale between atmosphere, vegetation, soil, and then very small percentage of them were dealing with what's going on deeper in the underground. Actually, we also found out that there is a lack of studies combining karstology and forestry. So there was not really a lot of studies dealing with the groundwater recharge processes, let alone studies done in the caves and so on. Maybe I can give you two examples of such studies. One was, for example, studying wind throw and connected pollution issues, and the other one was dealing with the drought and also how woody vegetation was uptaking water in connecting to the geological settings. And as I mentioned, we were really enthusiastic about making a study that would combine both knowledges, which obviously was lacking. So we selected our case study in southwestern Slovenia. A part of it you will visit tomorrow. It is the catchment of the Unica springs. One of these springs is also regionally important drinking water supply. And also in the catchment there are a lot of sites which are important as karst groundwater dependent ecosystems, such as intermittent lakes, cave systems, and so on. So the springs themselves are situated in the north of the map, and they are recharged by either autogenic karst water or by the rivers that are flowing through the non-karst area and then sinking and recharging the springs. And by the way, this area is also a bifurcational area. It is shown by these gray arrows how proved groundwater flow connections are flowing, and those that are flowing towards the north are flowing towards the Danube system, and those that are flowing towards the north or towards the west, they are recharging the Adriatic Sea. The catchment of the Unica Springs, which is about 800 square kilometers large, is mostly covered by forest. These are these green patches, and in the period between 2014 and 2018, several series of large-scale forest disturbances occurred. First, there was this ice breakage, then bark beetle infestations occurred, and afterwards there was also wind throws. So in this period, 2/3 of the forest was damaged. This is mapped by these strikes. And also a lot of wood stock was lost. We focused our study in the northern part of the catchment, where the cave system of Postona and Planina caves occur. There is the Dinaric fir beech and hornbeam forest. And I have to stress it's a natural forest there. And there are also Renzina and chromic Cambi soils, typical karstic soils occurring in the area. We have established monitoring points on the surface, which here are marked with the red dots, and also in the underground, in the caves, marked with the green dots. Our idea was to observe the system through the so-called karst critical zone. It's a modern term. But anyway, the idea was that we monitor several spheres from the atmosphere, vegetation, soil, and then go into the underground, into the unsaturated zone of the aquifer. We established continuous monitoring of the meteorological and hydrogeological parameters starting from October 2020, and I will now present you the results of the 2 years monitoring. Maybe some photos how these monitoring points looked like. There are 10 points on the surface. The equipment was specially designed for this experiment, and we set up these monitoring points in order to cover several forest development phases, from the canopy gap to young forest and then mature forest. We also took special attention to the topography. So some of the monitoring points were in the depressions, in the lowlands, some on the plain, because we were also interested in the differences in topography. And then in the underground, we established 5 monitoring points. These are also different. Some of them were more larger, were more continuously dripping. Some of them were more, we call them lazy, and they were not responding to every precipitation event. Again, special designs for monitoring this was done. And on the surface, we monitored the precipitation and throughfall, soil temperature and soil moisture content. In the underground, water level or water dripping depends on the point, and also water temperature and electrical conductivity. These data we then used for the time series analysis, statistical analysis, and also some numerical modeling using several different models. About 2 years ago, we also conducted, I will try. We conducted a tracer test, if this will work, but it will not. I don't know what I pressed now. Anyway, you have to turn your head now. It's a method that we used for testing our hypothesis. We injected 200 grams of urine, it's an artificial tracer, into the crack above the monitoring points in the caves. The approximate sealing of so between injection point and monitoring point was more than 80 meters, and we of course then observed the cave drips in the cave to detect the tracer. And these are now the results, starting from the surface. These graphs are showing 3 monitoring points where the bars are the precipitation, and then the curves are showing water moisture content on different depths. The lighter blue is the 30 centimeter depth, and the darker blue is the 60 centimeter depth. And what you can see at the first glance, we can see that there is a distinction between seasons. We can see seasonality, right? And it is obvious that evapotranspiration effect is driving this seasonality. There is more moisture is greater during the vegetation dormant season, and it also increases with depth. The biggest differences are noticeable in the growing season, so these are these lower parts, and you can see also the spikes. The spikes are showing the reaction in soil moisture content after some precipitation event. And in 2022 is this drought season that we also mentioned before. Well, the soil moisture content starts to increase with the time lag between 5 to 16 hours after the precipitation onset. But this also depends on the type of precipitation, event intensity, duration, and so on, and also on the monitoring point itself. We can also see that the greater differences in soil moisture is in areas with younger and mature forest, so canopy gap. There the moisture values are different. Both soil depths are more similar. Then also soil moisture reactions are more frequently occurring in the vegetation dormant season. These are these yellow bars showing. But this is not what we expected this results. And interesting was also for us that in the lines, less reactions occur. Again, there were some differences when we did some statistical analysis which show us that in mature forest and in canopy gap areas, statistically significant increase in soil moisture was in the vegetation dormant period. And we explained this with less intensive evapotranspiration. However, in the young forest areas, there was the statistically significant increase in soil moisture in the vegetation growing period. And again, we found, or we explained this with the canopy interception, which might be the cause of that. Also, I would like to attract your attention to the differences between the circumstances in the lines, in the depressions, and what happens on the, we call it plain, so not depressive part of the topography. Here are shown the curves of both locations, and we can immediately also see that the high moisture content is in the lines, and these points also take longer to react. They react less intensively, and they have not so steep slopes, and also they have longer tailing in soil water moisture content. And now I will leave you a few moments to enjoy what is going on in the underground. Excuse me, I need some water. And Chairman, how am I with I'm okay with time, right? I mean in time. So I will now take you in the underground. The drips that we observed, they did not react to every precipitation event. Only about half of the precipitation events caused the reaction of the drips. And these differences are related both to the characteristics of the precipitation event, but also to the hydrological conditions that were present before the event. Was it more dry or more wet situation? And also there are differences in the degree of karstification of the rock, the thickness of the ceiling above our monitoring point, and so on. But in general, the average quantity of rain that was required for the drip to react was between 20 and 34 millimeters of rain. There were also differences between both of the caves. For example, the Planina cave, there the drips were more reactive. They reacted more often and also in higher intensities, while on contrary, the drips in Postojna cave, they needed more rain, they needed more time to react. So regarding the time lag after the precipitation in Planina cave, they needed between 9 to 15 hours to react, while in Postojna cave, they needed a day or day and a half. And also another interesting thing that we observed was that the majority of drips responded to precipitation in the vegetation dormant season, which also correlates to the situation that I described before with the soil moisture content. Then also, during the vegetation dormant season, the proportion of responses were higher after the hydrologically dry period than during the vegetation growing season. During the vegetation growing season, the drips needed 6 times more precipitation to react. Then we considered that evapotranspiration is the main driving force to cause this kind of behavior. And we also wanted to test this hypothesis with modeling. But with Brook 90 model, we also confirmed our hypothesis that in the growing season, evapotranspiration is much higher, as you can see from the bars above, on the above picture, while in the vegetation dormant season, this is a bit lower. And as a result, also in the growing season, effective precipitation is lower. And one interesting thing also was that evapotranspiration is the highest in young forest stands. So young forest really needs more water, and also there is more canopy interception because the leaves are coming in layers. There is a succession of leaves and so on. But it was also interesting that this is the highest is evapotranspiration in the dowlands with the young forest. This also surprised us. On the yearly basis, we can see that the lowest effective precipitation is in the dowlands with young forest, and the highest effective precipitation is in the canopy gap. Now, this is one result that has the implications for our question at the beginning of our study. So if the vegetation cover change impacts the recharge. And in one of the previous studies, we also made an investigation on the catchment level of the same area. We did some climate change, climate parameters trend analysis, and then we also made some comparison of estimated daily values of effective precipitation that takes into account the vegetation cover change with the, we compared it with the estimated effective precipitation values, which doesn't assume the vegetation cover change. And again, according to the climatological trends, we expected higher decrease of the discharge of the observed springs, but these springs did not have so much lower decrease of the discharge. And the comparison of effective precipitation showed that in the period of the large-scale forest disturbances, the effective precipitation increased for 5%, which also then caused higher, or actually it milded the effects of the climate change parameters changes. And we can also conclude that large-scale forest disturbances caused smaller decrease of mean discharges of the spring than expected. Then we also tested what does this mean in the karst aquifer itself, disregarding the soil and vegetation cover. We also did some modeling, and where we combined different conduits of different hydraulic conductivity, and this modeling showed us that fast transfer occurs in the very conductive parts of the system, while delayed transfer is then occurring in the smaller fractures, which can also last for weeks or even years, as we heard from the previous presentation. And this was also then confirmed with the tracer test. Namely, our tracer test results showed that 7 hours after the injection, we were able to detect the tracer in the cave. And we conclude with this experience that vegetation cover has significant influence on how karst aquifers are recharged, and also that large-scale forest disturbances might accelerate the infiltration on one side, but on the other side they may cause smaller filtering of the pollutants, and in this way the quantity and quality of the water may be threatened. This is the first comprehensive study of this kind, and although we know it's a site-specific, and although maybe positioning of the monitoring points on different places would, due to heterogeneity of the karst, show different results, we still think it is an important aspect to take into consideration also vegetation cover changes when protecting water and environment. And with this, I would like to thank you for your attention.
So thank you very much for your presentation. Just time for a very short question. If not, then I would like to thank you again. And we shall proceed to the
Thank
next
you.
speaker. And this is Professor Bojan Mohar of the Department of Mathematics, Simon Fraser University from Canada, and Department of Mathematics, University of Ljubljana. And he will speak about Slovenia modeling karstic aquifers using network theory. Please, the floor is yours.
Thank you. Thank you, Professor Stanovnik, for inviting me to this interesting event that I've been enjoying so far. I know I'm towards one of the almost last speakers of this session, and you must be tired, but I hope we can still go through whatever I want to talk. So I'm a mathematician, so I'm theoretician. I do theoretical work, fundamental research, making proofs in mathematics, and now I came to speaking about karst and water resources. So how was that? It's basically, I was attracted to a group which started with a European Research Council synergy project, and here are the principal investigators of this. So I'm the synergetic part, bringing mathematics into this area. So, and today I would like to just briefly touch what we will be doing in this project. So, what are the challenges, and what is one of the issues I think I will be able to do something. So something about networks, how these specific networks about karst develop, how they can be treated and used for maybe forecasting or water or doing with water resources. I'm happy that we also include Franci Gabrovšek as an additional member of this great team of international researchers. So this picture just shows the diversity of the principal investigators. For instance, Marko Densis is working on solute transport in unstructured media, and it's doing things which other members are not so familiar with, and so on. But let me just start with karst aquifers. So why are they different from usual aquifers? First of all, a lot of it is underground. And a lot of it has been said already in this session, so I'm not going. But one thing is that karst is present almost everywhere around the world. So it's a lot of different or seemingly the same karst phenomena occur throughout the world. And another thing is that karstic aquifers are really important source of drinking water. Well, not only drinking, also for industrial use and so on, but it is an important fact that we would like to tackle here. Now, when I speak about karst conduits, and a network of karst conduits which discharges this water from sources to sinks, from sinks to sources, we can use usual models for networks like river networks on the ground. But karst has different specifics. So one particular specific is that description of karstic networks involves different scales of, so it is very multi-scale. You start on the left from a rock matrix or porous materials where the water drips through small pipes which you could say are on the millimeter side or even smaller. And then the usual main conduit network of karstic is made of caves and conduits underground. So this is on a meter scale. And then the whole network, you can say it's on a kilometer scales. So how can you, so one challenge that we want to do is to merge these different multi-scale descriptions into a single object, which is more complicated. So that's a basic challenge in describing karst networks. Another thing is already just on the conduit scale, it's that the physics is not really so well understood. So the flow of water, mathematically, you can describe it by partial differential equations and so on, but the solutions are very difficult. So usually it's only numerics is used, so you cannot get explicit solutions. And moreover, all this depends on the geometry of the pipes. So if you have a usual pipes in a city, they are very flat, very nice, and you can measure, you can use the basic physical laws to describe the velocities of the flow through these pipes. But here we have a very complex geometric diversity in the conduits. So not only that they are not straight, also the surface is not so smooth everywhere and so on. So, and one thing that we will gonna do is try to understand how this geometry affects the flow. And also another issue is this pollutant transport, which is kind of just mimicked here with this little graph from some measurements of pollutant transport. Now when you go to the whole network, underground network of conduits and caves where the water flows, you get different kinds. So this is from a study. This is from a study about 10 years ago, where the authors described different karstic networks all over the world, and you see a familiar picture. You see something that you would somehow say, oh yeah, this could be a network of caves where the water flows from the source to the sinks. But how do we do? We don't know usually these networks. These are underground. These networks are underground, and so our goal is to simulate the structure of the networks. And the last challenge is the upscaling. So you can observe, you can measure the water flow on a small scale, maybe in one conduit or next to the source. You can measure the flow here. You can measure the flow here. But what can you say about the whole network? So is there anything that a mathematician or a physicist could say how this will behave? So that's the upscaling challenge, which also we plan to tackle. So that's the the rough description of the project we gonna do. So we want to understand this very firmly, with physical laws at the conduit scale. Based on that, we would like to say, well, can we do a numerical model, and which can also be used on the network, on the whole network, and do the upscaling with that. The other problem is that we don't know the network, so we would like to say, what is the karst network structure? We must do some stochastic approximations for that. So that's the final outcome, of course. This is the future. So that's where also some of the previous speakers touched this. How can we use this to so that the politicians or the water management people will be able to do something, to say what will happen if we have a long drought, or if we have large rain coming. Now, I will now just take a few words about stochastic modeling of karst waterways. So why is this necessary? First of all, you can describe the water flow from the top, where you can observe how much precipitation we have. You can observe where the water disappears underground, and you can measure that, and then you can see at the spring how much water comes out. So these are the measurements which are accessible. Of course, you can also go underground if you have a hole, so you can go underground and see and put instruments in there and measure in there. Even when you have the water flow with this part where the water is under the water level, you can also do some submerging and measure things there. But most of the water network is unknown. So that's the challenge. People used basically the classical one is to do the tracer tests. For instance, you put the colored chemical, and then you see you measure where this colored water comes out, and this gives you just the connectivity. It doesn't say how the waterways go, but it shows, oh yeah, from here there is a connectivity to this part of the water system. So that's this is what we can do. We can actually drill, but this drilling is very sparse. So you're very unlikely to hit the conduit underground, right? So so this will give some additional information, but it's not so important. And so this our aim is to model this karstic network, which we don't see, and see how we do this with mathematical tools. So luckily, Franci Gabroszek already told a little bit about that. So here are just pictures of several works in the last maybe 30 years, which tried to use mathematical techniques to model these networks. You've seen today a picture like this. You've seen pictures like this. You can say also that would be. So these are the published results, and they describe a kind of water networks, and you can ask how good they are. So I think I skip this slide because I don't have. So there is. This is part of one of our researchers, Philippe Renard, with co-authors. So they did some kind of so-called MPS modeling, but basically, when we go to the modeling of karstic systems, we collect data that are visible to us. So data on the surface, geological information, so what are the geological composition on one spot. We do maybe the tracing and so on, and we make a geological model, and based on that, we would like to predict how the network looks like. And then you can use this, you can predict what the fractures would be and how the network would develop. So Franci Gabroszek gave a good explanation in his talk about this. So this is what is coming as a result. You get something, you predict there will be something, and you want to say, okay, this is close what it should be underground. And then can I use this? So here are some results from the literature. So the people got generated possible networks based on the input data, and so what? How close are they to the real data? That's difficult to say, right? That's very difficult to say. So as of course, we could use some statistical data to see that, and this is my last point that I would like to make. Is suppose that with some geometric random model, we construct maybe something which we believe it's our karstic waterways system, and how good it is. So here is just a short example. Oh, these are some more examples that I mentioned, also appeared in the literature. So and this is back to the picture we've seen before with more types. So here are some types of concrete networks known in the world. So like there could be, one of them could be the Postojna cave system, so that we've seen before. So, and there are there are others. I don't think Postojna is here, but it could be. So you can see the systems. Now, what we do is, on a case study, we look at our geological information and we say, oh yeah, our mathematical model tells me the karst system should be like this. And then I get a result. So let me skip this for a moment. And then I get a result. It could be the system on the left or this one. So here, basically, the naked eye will say which one is more realistic, right? The one on the right looks like the real cave system. The one on the left looks like a fake cave system or conduit system in the world. So how would you do this automatically? Well, what was done before with was that we tried the following. So you measure certain measures on the graph that you have, on the network that you have. So here are just maybe the average distance across the network. So you look at any two nodes of the network and see what is the distance between them. So what is the average distance? So this is this parameter here. And there was a testing of some other parameters. So this was just a quality check, just one specific check. And then when you come to these two networks that we have here, you can see that the values, the numerical values, the red dots here, were in here. So what is the blue range? The blue interval is are these numerical values for the known systems from these ones. So you take from these ones, and then you look, is my numerics on this network, is it the same or not? So here it was outside of the interval, here it was in the interval, and you see the fake network really gets a different result. So here is within the expected range of these parameters. So that's a way how you would somehow test if your network is kind of realistic or not. Of course, there are other things that we'll do. So we just started with this project this year, and I hope that maybe in a couple of years I will come with with more results and more outcomes of this project. Thank you very much.
Thank you very much, Professor Mocha, for a different approach to the program. So, yes, please, Professor Meinzer.
Thank you very much for this exciting talk, because it is on the line on complex system modeling, which we touched for several times this morning. Now, what was very exciting for me here, for my own research, are your last slides, because what you illustrated to us was a kind of database of different possible networks, examples. And that is also known, this approach, for example, in chemistry, namely bounds, special bounds, a database of special bounds in chemistry. Now, my question is in the direction of machine learning. That means modern machine learning, supervised learning algorithms mean that at first we train the neural network with these kind of samples. And then the network, by supervised learning, because it is trained with certain prototypes, is able in pattern recognition to make suggestions of probable networks on the basis of these samples. So the question is, how far these ML machine learning techniques are used by your approach?
We didn't use this so far, so it's of course machine learning is doing a lot of these things, and what I just touched at the end, it was a kind of idea. So not the pattern recognition, but it was a simpler one, well, just numeric invariant recognition. And of course, definitely there is a future in that too. Yeah.
So thank you very much, Professor Mocha, again. And the last contribution of this morning session is by Professor Milan Radulovic from the Committee for Geology and Geography, Montenegrin Academy of Sciences and Arts, and Faculty of Civil Engineering, University of Montenegro. And he will speak about karst hydrogeology of Montenegro. Professor Radulovic, the floor is yours.
Thanks. Hello, everyone. Today I'm going to talk about karst hydrogeology of Montenegro. In first part of presentation, I will speak about hydrogeological characteristics, and then I will show a state of groundwater monitoring network in Montenegro, and I will show some results of water budget. I will show some interesting values. You know maybe that northern part of Montenegro belongs to Danube River Basin, and southern part to Adriatic Sea Basin. The main rivers that flows to the Danube River Basin are Piva River, Tara River, Čehotina, Ibar, and Lim River. And the main rivers of southern part are Zeta and Morača rivers. And the Bojana River outflow of Skadar Lake is one of the largest river of Adriatic coast. Geology of Montenegro is relatively complex, especially in the southern part along the coast. It is divided in 4 tectonic zones, but the interesting one from a hydrogeological point of view is Visoki Krš zone, high karst zone, which is distributed in central and northwestern part of Montenegro. From this hydrogeological map, you can see that karst aquifer has the dominant distribution, here represented by yellow. It is represented by limestone and dolomite, carbonate rocks, but for us is also very important intergranular aquifer represented by blue, especially intergranular aquifer of Zeta Valley in the central part of the country here, because that is one of the richest reservoir of groundwater in the region. During the summertime, we pump around 3,000 liters per second, especially for water supply and irrigation of vineyards in Zeta Valley. Really very rich aquifer, and in the northeastern part, we have impermeable rocks, maybe mainly shells and flesh sediments. From this block diagram, you could easily understand recharge of karst aquifer and discharge zones along the coast. The main recharge zones are on karst plateaus, especially here in Orient Plateau, where we have a huge amount of precipitation. Around 5,000 millimeters per year is measured in one station. That is really huge amount comparison with London, that is 8 times higher precipitation rate than in Northern Europe. Also, discharge zones are distributed mainly along the coast, and we have also many submarine springs. That is one of the problems during the summer, because we cannot use that water because salt water intrusion is increased in that period of year. Probably from Slovenia you recognize similar terrains that are karst plateaus with many dolines and uvalas. And here we have one paradox. That is that we have a largest amount of precipitation, but there is no any surface water, there are no any stream. During the summer time we have no any drop of water in that zone. And farmers must drill deep wells, sometimes around 400 meters to reach the groundwater level, what is inefficient because that wells are very expensive for them, and also to pump water for such depths is also inefficient. But sometimes, that's not often, in that zones we have more water that we want to have. That is Cetinje polje. During the last big floods in 1986, when we have in same time snow melting and intensive precipitation. And the inflow of water to the polje was higher than the capacity of swallow holes in another part of polje. One of the main problems for us in Montenegro is to delineate catchment areas of springs. That is important because we must protect that areas from pollution to be sure that we have fresh and clean water at springs. We use almost all known techniques from the water budget calculations, tracer tests, isotopic techniques, also modeling, but after all, again, we cannot be sure where that boundaries of catchment areas. We can assume based on results, but again, the certain degree of uncertainty is always present. Here you can see the connections between swallow holes and springs, and that results are very useful for us to protect groundwater from pollution. Here is one cross-section from Lovćen to Crnovića spring along one of established hydraulic connection, and from swallow hole in Cetinje, tracer flows around 2 days to Crnovića spring. And the highest velocity of tracer which we measured is around 11 kilometers per day from Grahovo polje to Risan Bay. And from the hydrograph, you can see that ratio between minimum and maximum discharge is relatively high, around 1 per 50, and the reaction of discharge to precipitation impulse is also quickly what tell us that permeability of rocks is high. Here is one interesting spring in Boca Bay, that is temporal spring Sopot. There is a huge amount of water after intense rainfall, but we have sometimes situation in same day to have water in the cave, but in the same day to dry up almost completely. And another part of water from that aquifer is discharged via submarine springs. But unfortunately, the springs are not useful for water supply because the concentration of chlorine is increased during the summer. I will briefly show the state of monitoring network. In last 5 years, we improved our monitoring network, and we drilled around 30 new boreholes where we installed probes with data loggers, and we now have relatively good system for monitoring with remote transmission of data to the central office. And here you can see one of the interface of software which we use it for continuous monitoring, but also we are taking 2 to 4 samples per station per year, especially one from September and October when we have the worst situation regarding the groundwater quality. And there are parameters which we measure. Generally in Montenegro we have a good quality of water. There are some events after intense rainfall, the turbidity of water is increased. Also the bacteriological content is increased after the rainfall, but generally water is good quality. There is one of the worst point in Zeta Valley where we have increased concentration of nitrates, but that is expected because in the hinterland of that point there are a lot of vineyards and agriculture area where mineral fertilizers are used. And if we speak about the average values, we can freely say that Montenegro is very rich with water. The specific runoff is around 43 liters per second per square kilometer, but after all presentation, you understood why it is not good to look at the average values when we speak about karst. Here in Slovenia, also in Montenegro, the increased temporal unevenness of water resources is present. During the winter we have floods, but during the summertime many of springs are dry. Also in Montenegro we have that paradox that around 30% of the country is waterless. In that karstic areas we have a huge amount of precipitation, but we are free to say that we have desert in sense of what availability of water resources in the 30% of the area. But hopefully at the lowest points at the populated area we will have enough water for water supply in the future. Now 92% of water supply is based on the groundwater, especially karst aquifer, and we are sure that in the future will be good situation regarding the quantity, but we must find ways how to protect that water for populated areas and how to protect that really precious water resource. Thank you.
Thank you very much, Professor Vakilovic. And now I hope that you will be willing to answer the questions, if any.
Just one small question. Do you relate your submarine springs to, to changes of base levels after the Ice Age, or was there some relation with the Messinian crisis, like they showed in France or elsewhere?
There was few studies, just from the period of Johann Switch, from the beginning of 19th century, we had a few understandings how that water network was functioned in the area of Boca Bay. There was few rivers which flow through the today bay, but after the increase of water level, we now have submarine springs, and also during the bathymetric survey we detected some canyons below the seawater level. So I hope that is interesting question, and I think that could give us some answers regarding the submarine springs.
Another question.
Just interesting, since when these undersea water springs are known? When were discovered? I mean,
Yeah, that's good question. Sometimes on the huge springs we have circular sign on the surface of water, but remote sensing is also useful for that. We use thermal cameras, and sometimes we can recognize dead zones where cold groundwater flows below the hotter seawater during the summer.
Yes,
One question. This region seems to be very well informed about karst theory. Is there cooperation between your countries? So do you have something like a group of karst meeting once a year or once a month and exchanging experiences?
Yes, we have this committee of geology and geography, and also there are a few conferences where we change our opinions about karst. Also, I'm thankful to SAZU because I started from 2006 to attend schools in Postojna, karst schools, and that was really good starting point for me, where I learned many things about karst.
Thank you.
Thank you.
Any other question? If not, then let me thank all the speakers of this morning and all to those who discussed the matter. Now is the time for lunch. The lunch will be served in a restaurant approximately 100 meters from here on the left side of this thing. And we shall assemble again at 2:30.
Thank you all for coming again. And we have one lecture less because one of the presenters is missing. The other one who is missing sent us a video record of his talk. So we will start with the talk of Professor Jovan Despotovic, who will tell us about the information to the authorities and local people along the Danube River concerning the flood regime, an empirical evaluation. So I will just leave the talk running and then we go back to our normal oral presentations.
Good morning, or good afternoon, better to say, to all of you, ladies and gentlemen. First of all, I would like to apologize for I haven't been presented in Ljubljana, but unfortunately I got corona infection, and I'm stuck in Belgrade. Next time, I promise I will come in Ljubljana, since I like being there. Today, I would like to share with you information received from different points and different sources in regard to water regime on the River Danube basin, together with some social and urbanistic and spatial planning information aiming at connection those two domains. And this is, to my experience, not sufficient for the local people and the authorities, particularly in small cities along the river Danube, where I've been engaged with some projects and study work measurements as well. And I would like to say that in front of the Serbian Academy of Science and Arts and UNESCO Intergovernmental Hydrological Program that I'm chairing in Serbia, and I've been representing the second group of the UNESCO Bureau and the Council for 4 years. The Central Europe, Central Asia, ex-Soviet republics and Balkan countries. And I gain experience from all of those watersheds and basins, and particularly on the river Danube. Just to remind you that Intergovernmental Hydrological Program of UNESCO started being coordinated in late 60s together with the Commission for Navigation in Budapest for floods also. And the Category 2 Center, Irkut UNESCO, was established in the year 1988, And last but not the least, the Secretariat of the National Committees of IHP UNESCO at the River Danube was established during Corona. Actually, it started being in function this year at the Faculty of Civil Engineering, that is a seat for all of the 3 mentioned institutions. At the beginning, I would like to share with you the experience gained in UNESCO IHP for decades within the family of many centers and chairs, because in recent years arose a lot of problems within climate change. One of those is water having a lot of force and strength in many occasions in the world, presented in floods, disasters, and very strong, unpleasant way of management for water. And on the other hand, we have to be aware of the watershed approach, the basin-wise approach, which is always not very well known from 16th or 15th century, but it is getting more and more important. And this is why the first proverb, water, water everywhere, only if you share, won the contest in the UN water sector in 2013 by a young girl from India, Kumar. But we added to that part of the sentence that goals, knowledge, planning, projects, responsibilities, and benefits should also be shared at the watershed or basin scale. Another issue which arose with problems with climate change, which have been happening for decades, and extremes we've been facing for the last 10 or 20 years, is that every drop should be paid attention to, which says every drop counts, concerning particularly climate change, including floods and droughts. So we are aware of that, and we have to accomplish, reanalyze, and redo all of our river basin management plans and integrated water resources management on a base level or on the city level. And this is something which is very much concerned the world and each and every person. Contents of this short presentation will be based on the experience gained with the analysis of historical floods on the river Danube and analysis of flooding areas along the Danube and its tributaries. Then protected areas and flood risk assessment is also an issue. But on the other hand, a lot of those of analysis and general design projects and studies are not approaching everyday people, small cities, small authorities. So we are concerned if there is a possibility to share those information with everyday problems of people in cities, in rural areas, accounting for everyday life. This is why we try to connect it with the cross-border cooperation, with heritage-based tourism, including bicycle and rambler roads, and particularly of public education of people and authorities concerning floods, accessibility to water for drinking purposes, for irrigation, small industries and manufacturers. So I would like to pay your attention to potentials of this meeting of academies to think about preparing some project fish or some study work of terms of reference for some project that will be coordinated by top experts in order to get more value and more information to get it more value to ordinary people in the field, everywhere, in cities and rural areas, in large cities, etc., to an equal or similar to equal degree of reliability. Just to remind you that the river Danube basin is of approximately 870,000 square kilometers, shared by 19 countries, and this is the second largest in Europe. But in each and every part of it, we have to we have to provide information to people, to authorities, local or national or regional, about the availability of water and threats of water that people are aware of that. There are several major documents among many of those that we consulted and analyzed for this presentation. One or two are from the domain of water and floods, and the two of those are concerning urbanism and resilience, accounting for Danube cultural heritage. So this is performed by coordination of the Faculty of Architecture in Belgrade, together with several other countries' institutions. The conclusions stem from those documents could be explained in brief in the following way. Floods occurred in the last millennium, which was analyzed by the group of IHP committees I mentioned before, in many occurrences from 11th to 21st century. It could be found in details in the reference now, reference 1. But generally, the area of the basin Danube was divided in upstream area between Passau and Bratislava, middle and lower Danube. What had happened, and what is very much important for high historical flows, is that in year 1501, 1887, it's a mistake, 2006, 2014, which could be seen on the next slides, occurred 2 times or 3 times the flows of approximately 20,000 cubic meters per second, which is very much close to the statistical 500-year return period flow, was approximately also 20,000 cubic meters per second, which is not that peculiar, as it could be concluded at first moment, because this is some kind of a quality quality of data that we took for this. It was taken for the consideration, and quantity of data which was taken into this consideration, accounting for numerous re-engaged stations along the river Danube. This is something very strange and something that we have to be aware of. We've been facing in person floods in 2000, 2005, 2006, 2010, 2014 and 15, out of which the one that happened in 2014 in the area of Croatia, Bosnia and Herzegovina and Serbia was disastrous, with a lot of casualties, dead people, and enormous damages in billiards of euros. So after that, there were also some disasters and floods in smaller sub-basins, like in Slovenia or Croatia, on some other parts of Serbia. So we have to be aware that there is a threat, there is a big threat of large rivers, large flows on the river Danube. There are 2 chosen flooding events along the Danube in earlier years, 1954 along the Danube and 2006. 2006, I must admit that I faced in Belgrade and in some part of Croatia and Bosnia, and I was really frightened. When we compare it to the other big floods that happened in 1501, which we haven't faced, and in 1897, which was depicted in the famous novel The Bridge on the Drina by the Nobel Prize winner Ivo Andrić, and we saw the traces of that floods on the bridge on the river Drina, and in comparison to what happened 9 years ago, 2014, in the area of Serbia. So we are pretty much unaware how it looked like before it happened in 2014. I must admit that there is a need for much stronger cooperation in the field of water in the basin of Danube, but not only in water domain. To my experience, I think that it is very much important to connect all of the domains of people activities and economy, accounting for irrigation, navigation, water supply, hydroelectric power industry along the Danube, to coordinate and to save some space for floods in the future. Damages and the casualties are very much, and in Serbia it can be counted in billions of euros each time it happened. We had a similar situation, not that difficult and and dangerous like it was in 2014 last summer, and it was counted in couple of hundreds of millions of euros, and this started being more and more expensive and more dangerous to people. So we would like to be aware that this is something increasing with the increasing of the extremes more and more. In addition, there are some other studies performed at the Danube basin, accounting for quality of water, done by ICPDR from seated in Vienna, and protection of living world at the Danube catchment is something which is very much important, but also connected to high levels and high waters, high velocities, and very important high forces on the bottom and on the riverbed for living world. I think that this information should be spread to let's say lower and wider audience and societies in small cities, medium-sized cities, and everywhere, because people should know what it could be dangerous and what is already dangerous what was dangerous in history. In this regard, we think that education have to be organized in more detailed and much more locations, education for pupils, students, and people, not only to those who are responsible for that, but also to those who are in connection with water, either on their fields or in rural areas or in cities, but to be concerned about the floods, and on the other side, to be aware of droughts. So more educational camps should be established in natural parks or protected areas for collecting people and experts, aiming at exchange of experience within continuous education and improved flood protection. This is a map of ICPDR presented in 2015 or 16 for flood risk and protected areas. On the other hand, there is a lot of hidden urban, cultural, historical values along the Danube, which was depicted within the cooperation in the Interreg program under the coordination of the Faculty of Architecture in Belgrade, but not only within this, and all the other different programs in the area, accounting for bicycles, ramblers, etc. And this is something that could help in understanding and mutual support of people, small communities and cities in the field of water protection. There is a map of the cities and towns in the middle and lower Danube region that were in the game of this Interreg program. From that document, we found certain conclusions should be emphasized and meetings for action plans, where those who are interested in preparing their participation in the program should be depicted and described to a certain important peculiarities for each of those. And in this regard, we can collect some, let's say, a puzzle of the activities and at different locations and different parts of the river basin. Some of those are cities of Bačka Palanka and Ilok, actually connected with the river Danube, and very much famous old fortress of Golubac, renovated in recent years, and one of the most important and very nice fortress at the river Danube. At the end, we would like to pose a couple of questions for all of you or all of us, for people and treasures at the river Danube, to be some kind of a background for further cooperation and communication, possibly within the Interreg or some other regional European projects, and how to improve living conditions for people and how to protect cultural and historical heritage and treasures in the area. Potential answers and some conclusions are some kind of a mixture of those what we gained and what we would like to gain. In order to connect experience gained already, threats possible, and visions how to cope in a better way with some problems, fears, threats, and how to foundate frequent and much fruitful communication between all participants and stakeholders. But not only of those people as well, in the small cities, people in villages, people everywhere. Thank you for your attention.
Unfortunately, we cannot ask Professor Despotovic, but I would still leave a place if somebody has some comment maybe related to the talk. You can say, if there are none, then we continue with our next presentation by Lenka Hajarova from the Geotechnical Institute of the Slovak Academy of Science on the technologies in contaminated water treatment in Rye Island. So I think you just have to close this one. Yeah, exactly. So please go.
Okay, so good afternoon, everyone, and thank you for the kind introduction. So let me introduce our work dealing with wastewater treatment technology that is designed to protect this groundwater reservoir in the Central Europe, Rye Island. Rye Island lies between two arms of the river, this river, the Danube, divides just below the capital city Bratislava. It's between the Danube and the Little Danube. This area covers 2,000 square kilometers and represents 4% of the Slovak territory. The usable drinking water capacity of this area could supply more than 16 million inhabitants at the current average consumption. But the Slovakia's largest sources of drinkable water are threatened by many potential contamination. And during this presentation, I will talk about the Vrakuňa and this landfill in this area. But of course, this area of Ray Island is threatened by other industrial activities in Bratislava. So this landfill in Vrakuňa was made by dumping chemical waste from the former Juraj Dimitrov's chemical plant, and this waste was transferred into the dry channel of the original mill arm. Later, this waste was covered with the protective layers of soils. This landfill represents an area where approximately 120 cubic meters of waste from this chemical industry is buried beneath the surface, and composition of this chemical waste consists of explosive fertilizers, pesticides, herbicides, rubber chemicals, solvents, sulfuric acid, etc. This landfill has not been remediated nor isolated ever since. After the Gabčíkovo dam on the Danube was commissioned, the groundwater level began to rise, causing it to reach the chemical waste landfill ground. At the point of the contact, pollutants are leached and enter the groundwater. It has been measured that these toxic substances flow at the rate from 300 to 500 meters per year right into this area of Ray Island. On the basis of screening and modeling results of this contamination spreading, it has been shown that some pollutants threaten the quality of groundwater in Vrakuňa, Ružinov, and Podbanické Biskupice and penetrate further into the Ray Island. The Slovak Academy of Sciences, together with partners, focus on improving these conditions of this area by searching suitable decontamination methods, and the main attention was paid on elimination of organic pollution. The chemical composition of this contamination is diversified and can be classified into several main groups, like chlorinated polycyclic aromatic hydrocarbons, phenolic compounds, rubber chemicals based mainly on benzothiazole, and also accompanying contaminants of inorganic nature, like heavy and heavy metals, are also taken into account. The presence of 965 substances in the groundwater samples was confirmed, where 282 were identified and represent approximately 90% of all organic matter detected in this groundwater. For this comprehensive identification, we use combination of separation and identification methods like liquid chromatography, gas chromatography together with mass detection. So remediation of this environmental burden will be implemented in two phases. The first one, isolation of this pollution through the construction of an underground sealing wall and also surface sealing layer. And the next one, remediation of contaminated groundwater, which will be pumped from the landfill body. Due to the fact that these surfactants and solvents were also deposited at this landfill, conditions were created for dissolution of these contaminants to create abnormal and extreme concentration of this contamination. This water pumping after isolation of this landfill has to be carried out for a long period of time, decades, in order to create a hydraulic depression in the landfill body. This hydraulic depression and lowering this level of groundwater will make it possible to prevent the contaminated water from flowing out from this landfill body. So the quality of the treated water after this treatment has to be close to the quality of the drinking water. And it is possible to achieve by traditional methods like precipitation with precipitation agents or capturing on various adsorption materials. But concentrated material together with sorbents must be then chemically stabilized and also landfilled. The proposed technology will use two basic principles to remove contaminants from this groundwater. separation processes in which the pollutant is separated from the matrix, and also destructive processes in which organic substances are decomposed into inorganic products like carbon dioxide, water, nitrates, sulfates, and chlorides, etc. So, due to the nature of this contamination, electrochemical oxidation will be used as the carrier method. This method is suitable for the treatment of waters containing persistent organic substances or highly toxic substances. Strong oxidizing agents based on active oxygen, chlorine, and other elements are formed on the surface of electrodes and also in solution from the substances present in the electrolyte. These oxidizing agents cause transformation and degradation of these organic molecules up to complete mineralization to carbon dioxide and inorganic products. Before the actual electrolysis, this water sample was pretreated by water stripping. So we used electrochemical reactor with a working volume of 1 liter, and production of carbon dioxide was monitored during this electrochemical process, as the carbon dioxide is the final product of this decomposition of organic compounds. During this process also samples were taken for chemical analysis like liquid and ion chromatography and also total organic carbon or chemical oxidation demand. And this graph shows the change of chemical oxidation demand, indicates elimination of these organic substances and also significant decrease of total organic carbon. This slide presents output of this analysis of organic substances by liquid chromatography and mass spectrometry before the actual electrolysis. And some of these detected organic compounds are listed in this table. Many of them are insecticides or pesticides, like for example these gamma and delta hexahexanes, cyclohexanes, or for example prometrin, which is herbicide which inhibits photosynthesis or other enzymatic reaction. Concentration changes of selected substances during the mentioned electrochemical treatment are shown at this slide, where concentration of organic substances like hydroxypropazine or prometrin decreased, and on the other hand, concentration of inorganic products like sulfates or nitrates increased. Concentration of chlorine species is stable, where chloride ions are converted via chlorides to perchlorates. The proposed water treatment technology can be described as zero waste with no waste byproducts without sludge. The main advantage of this technology is that no chemicals are used, essentially only electricity is consumed. This technology also takes into account the specific physical-chemical parameters of this groundwater, like high alkalinity, carbonate hardness, content of non-polar or highly polar organic pollutants. So, author of this technology is Dr. Kupka. Unfortunately, he is not here, but I will do my best to present this technology. So the first stage is exploitation of contaminated water, where this groundwater will be pumped from the extraction well by a pump directly into the oxidation tank. So next step is aeration. Aeration with atmospheric air will be carried out in this oxidation tank, and also as the oxidation of organic substances. At the same time, this separation of volatiles will occur, as these volatile substances are transferred from this liquid phase into the gas phase. Also, a fume extractor device has to be installed above this oxidation tank to capture these volatiles. So another positive factor during this process is precipitation of solid precipitates, as these precipitates may cause colmatization of remediation equipment in subsequent stages. This colmatization is caused by precipitation of precipitates with calcium, iron, manganese, or magnesium. And after this precipitation and accumulation, the solid phase has to be removed, and it will result in water softening and subsequently in a high efficiency of membrane filtration and electrolysis in subsequent stages. So next step is sedimentation of this solid phase to separate and capture the solids. And after that, this pretreated water enters the reverse osmosis system. This system separates filtrate and concentrate into different volume ratios. These ratios can be controlled by adjusting the pressure. Filtrate will be then purified by UV lamp and also suitable adsorbents, and concentrate will enter electrolysis. So reverse osmosis causes reduction in the volume of treated water and increases the concentration of contaminants in the concentrate. So this concentrate is pumped or will be pumped into this electrolysis circuit, and these oxidizing agents cause transformation of organic molecules up to complete mineralization to carbon dioxide and inorganic products. In this picture is shown electrochemical reactor in our laboratory. We use cells designed for large volume flow with low pollutant concentration and diamond-coated perforated plate electrodes. Next step is adsorption, where this multi-stage absorption filter consists of tank into which the treated water flows. And also during this pretreatment, a foam was produced. So because of that, a flotation column was created and patented in our institute. And to conclude, the presented water treatment technology is unique and use progressive technological procedures. This technology can be described as zero waste with no waste byproducts. And the main advantage of this technology is that no chemicals are used. In addition to this water treatment effect, the contaminants are destroyed on site. This technology is waste-free in terms of elimination of organic substances, and these carbonaceous components are transformed into carbon dioxide and inorganic products without the formation of toxic residues. This picture represents riparian forests, which are considered as the richest ecosystem in the Ray Island, and I'm glad that I had this opportunity to present to you this technology that is designed for protection of such an important area for Slovakia. So thank you for your attention, and I will now be happy to answer your questions or hear your insights.
Thank you very much, Lenka, for this interesting talk. Are there any questions for the audience? Yes?
You mentioned active chlorine to treat the waste materials. I suppose that you have in that waste also phenol and phenol derivatives. With active chlorine, you will get polychlorinated phenol derivatives. And these are very stable compounds. And on the other hand, they are also cancerogenic, or most of them are cancerogenic. Mm-hmm. So what you have done with this polychlorinated phenols?
In this case,
the same question applies also to 1,2,1,3,5 triazine derivatives, to so-called atrazine derivatives.
Okay, so I believe that this electrolysis is a process that can destroy all organic compounds, So in the end, we really have only this carbon dioxide and inorganic products, nano-organic.
Another question, it's a very interesting technology for cleaning up the water. And I think it's powerful, of course. Can create maybe with this technology also chemicals which are not detected in the moment, that's right. But one question, how long do you think will this definitely supply you with strange chemicals? Or the other question, is there any plan to go into the source and repair the situation at all? Because otherwise, maybe the next 100 years or longer, you have to work with these chemicals yeah, that's my question. Is there a plan to do something against the source?
Yes, so I can move back a little bit. Okay, so this technology is designed specially for this landfill. And this landfill is, of course, on the ground, but in this case, this pollutant enters the groundwater, and through this groundwater, it is moving towards the Ray Island. So we planned 2 phases. First one is isolation, so it will be construction around the landfill, and also the second stage is this technology. So we will use this physical barrier around the landfill and also continuously treated this water. This is technology that will be carried out for decades.
Attenuation, but it will be a long way. So if this case would be the barrier, we would take it away, because you will not be lucky with that. But I know the reality. I think
Okay, so
as you described it from the history.
yes, we try to avoid this transfer because we believe that we like to decompose these organic toxic substances and not only transfer them to another place.
It's good what you do, but
I know.
In the European Academy of Sciences, we have an honorable senator, and he is an entrepreneur from Austria. And in his company, they are using nanotechnology for pollution in order to isolate waste materials, even these resistant bacteria, which we know from hospitals and so on. And so it is done, as far as I know, I'm no chemist, but as far as I know, by nano materials, and he's underlining that, not by chemical substances. And do you know something about this approach in comparison with your
Well,
water cleaning?
unfortunately, I don't know this type of nanomaterials and using water treatment this way. But we also focus on treatment of mining waters, for example, as mining waters can contain still high concentration of materials, and it can be also like critical materials like cobalt, zinc, as they are still listed on the critical list of materials, and it's important not only for Slovakia and also for Europeans. So, for example, mining water is something that it's not only about cleaning and treatment, but also it could be a good source for material. Thank you.
So our next speaker is Professor Andrea Gottwein from Faculty of Chemistry at the University of Ljubljana, and she will present us emerging micropollutants in wastewaters.
Okay. Thank you very much for this kind introduction. As it has been said, I come from the University of Ljubljana, and I will try to present you a brief overview of emerging micropollutants in different types of wastewaters, and I will focus on some processes we are using in our lab. So, we are all aware that civilization has been in contact with the wastewater for a long time. They have been addressed already in the ancient Rome, in ancient Greece, and the very important invention from the point of the human health is, of course, water toilet, which unfortunately contributes a huge amount of the wastewaters to be dealing with and to be treated. The same is also true with the industrial wastewaters, because of course in the past industrial waters were very low in quantity, they were very simple in their composition, but nowadays due to a variety of different processes, separation techniques, addition of different reagents, and so we have very complex wastewaters which contains huge amount of different compounds. And if we are taking into account also the reactions between them, physicochemical, biological reactions, we can be sure that we have thousands of different compounds in the wastewaters. And these micro-constituents in the water, which are micro because of their low concentration, and they are not easy to detect, because we have to admit that with the development of the instrumentation, the appropriate techniques has been available for the past decades. We now found in municipal as well as industrial wastewaters different synthetic and naturally occurring hormones, flame retardants, different stabilizers, and all of possible additives which we used in our daily life and of course also in different industrial processes. And that simply means that we have to address a large number of chemically and physically completely different pollutants. At the same time, if we compare the number of chemicals which are in different databases, for example, in Chemical Abstract Service, at the moment there is more than 144 million of different chemical substances recorded, and that means that almost 12,000 new substances are added daily. And if we compare in year 2000, we have 17 millions of different compounds in the database. In 2010, we have 55, and now we have 144. That simply means that these compounds are more and more commercially available. They are used in different processes, and of course, as a result, they end somehow in different types of the wastewaters. Treatment of wastewaters nowadays is more or less defined, especially if we are talking about municipal wastewaters, because we have simple pre-treatment, or you can call it mechanical pre-treatment to remove larger parts, and then the central part is usually some kind of secondary or biological treatment. And then it is usually combined maybe with some tertiary treatment to remove additional pollutants, or more or less to remove nutrients, nitrogen and phosphorus, maybe some metals at this point. So we have a lot of problems when we are talking about micropollutants in the wastewaters to address. If we want to apply some advanced methods for removal this newly pollutant, we have to think where in the treatment system add additional treatment. Maybe somehow, sometimes it is better to start at the beginning, to add some additional treatment at the beginning, if we have some compounds which affect the later stages of the treatment, or maybe it is more convenient and cheaper to add additional stages after the central biological treatment. And we always have to think about what is the aim of our treatment. So maybe we will just concentrate the pollution, maybe we will absorb the certain molecules, or maybe our goal is completely destroy or transform these pollutants into carbon dioxide and water, if of course we are lucky. But usually we are not so lucky that we would be able to do something like that. So there is a variety of parameters which can be used for the characterization of different types of the wastewaters, but usually very important one is biodegradability and toxicity as two summary parameters which actually define biotreatability of the wastewater. That simply means if the water is biotreatable, then we will probably select some kind of biological treatment, because biological treatment is something we like because it mimics the natural processes in the environment, and we are pretty much sure that the result is going to be something non-hazardous for environment and non-toxic, of course. But we are usually, when we are talking about micropollutants, not so lucky, so we have to select some kind of other treatment methods. And in this case, advanced oxidation processes are usually very applicable because they have already been quite good researched, and they are used and proven to be efficient for the removal of different persistent compounds in drinking water as well as different types of the wastewaters. Their action is actually quite simple. The main idea is to produce hydroxy radical, which are very reactive and quite non-selective. And they are actually one of the strongest, or we can say the strongest technical applicable oxidant with oxidation potential 2.8 volts. And they can be usually quite easily generated on the site directly in the wastewater with addition of ozone or hydrogen peroxide. You can also use some catalysis, and you can combine it with UV light and other sources of the light. And usually we can get the best effect if we combine different processes, but those processes are more or less some kind of black boxes. That means that we have to try to treat our wastewater to get the best results. So the main idea is actually to convert some kind of organic compound into these harmless products like CO2, water, and of course simple acids. And as I said before, hydroxy radical is the main goal of these processes because it causes the fastest reaction, for example, in comparison to ozone, which has also strong oxidation potential. How to produce hydroxy radical, we have a variety of different options. We can have homogeneous or heterogeneous processes. We can combine peroxide, UV light, ozone, all three of them. We can add some kind of catalyst like titanium dioxide, and we can also use iron. We can enhance reaction with ultrasound or with UV light. And of course, we also can have much more strict conditions like wet air oxidation or supercritical wet air oxidation. But some of you would probably agree that these are not advanced oxidation processes, because general for the advanced oxidation processes, we have like some normal conditions. That means the normal temperature and normal ambient pressure, while these two processes are, of course, run at much elevated temperatures and pressures. Two or maybe some processes I would like to describe are very simple, and they can be actually applied for almost any wastewater. One of it is Fenton process, which has the mechanism which is not completely defined. The main idea is to use iron 2+ like catalysts and hydrogen peroxide as oxidant to form hydroxy radical, but its efficiency is quite dependent upon the concentration of both of them, as well as ratio among them, because if you add too much peroxide, it will destroy your formed hydroxy radicals. The process can be enhanced with the application of UV and visible light, which actually helps to return iron 3+ back into the more active iron 2+, so you actually have some kind of recovery of the catalyst within the system. This process is very efficient, but as a result, you form iron 3+, this typical rust color, and the formation of this sludge can be quite significant. Depends upon the concentration and the ratio of all of the compounds. So that means that you have to treat this hazardous waste after the process. And very popular is also zonation, which is applicable for the drinking water as well as for the treatment of the different types of the wastewaters. It is fast reaction, and its advantage is that you do not have any specific solid or any kind of wastes, but usually the final products are very simple organic compounds like different aldehydes, organic acids, so that means that they are very stable, and that usually means that it is not so bad idea after ozonation of the wastewaters to add the biological treatment, because microorganisms will be able quite quickly to remove these during ozonation formed products, and you will get quite nice mineralization of the pollutants. And of course, the problem of the ozone is because it has to be produced on the site from the air, oxygen, or the mixture of both of them. The ozonation is actually the process which is very dependent upon physicochemical conditions, because it means that you have to transfer the gas from the gaseous phase into the liquid phase. So the mass transfer and also the rate of the reaction, the rate of the oxidation of the organics, is controlled by the conditions on the phase. And this is the reason that it is not so easy to predict what will be the final rate of the reaction. The ozonation can be enhanced with the addition of the peroxide, because the hydrogen peroxide helps to form more hydroxy radicals, and that means that we fasten the reaction. But the problem is, if you add too much peroxide, it will destroy formed hydroxy radicals, so it has to be used to be added in the several points within the reactor. And we usually had longer reactors or combination with the membrane to increase the reaction and to significantly remove all the present micropollutants. And ozone can be also combined with UV light, because again, UV light will increase the formation of the peroxide, and then of course we have the same reactions as we mentioned them before. So we actually, with UV light, we form the peroxide within the system. And the main problem of the application of the UV light in the wastewaters is because they usually have some kind of particles, and you can imagine that the UV light, which would like to reach the micropollutant, has to pass the water. It can strongly absorb there. It can be scattered because of different particles. So in some cases, you have to design the reactor very carefully that you really have some kind effect of the UV light. And of course, you have to remove all of the particles as much as you can before the final treatment. I would like to conclude a little bit with our research. Lately, we are focusing mainly on different types of antibiotics, which are used for human and veterinary medicine, because, you know, antibiotics can cause a lot of problems in the environment because they can affect the non-target organisms. Some of them are acute or chronic, express acute or chronic toxicity. They are very persistent. Some of them can even bioaccumulate or biomagnify. And of course, they can help to develop different resistant genes in the environment, which can then be transferred between different species. But all of those impacts are strongly correlated to their physicochemical properties, of course, their structure, transport pathways in the environment, concentration, and this is all what affects their final environmental impact. So we have studied numerous types of antibiotics, and we use a variety of advanced oxidation processes. We try also to determine different byproducts. This is the case of the thiamulin. Thiamulin is veterinary antibiotic, which is used for pigs and chicken. And we achieved very good removal using different oxidation processes, but the final toxicity remains after the treatment, and we identify, here is just 6 different products, but actually in some cases we identified more than 25 different products. So it's really very hard to say that those processes are efficient, because you achieved in some cases 99.9 removal, but actually there is a lot of different compounds present here. So we try to improve our advanced oxidation processes with the use of hydrodynamic cavitation, which is actually something which is caused by the fast movement of the liquid. It can be caused by a movement of the liquid, or ultrasound, or fast movement of the particles or radiation. And we know all of these effects from, example, corrosion of the ship propellers because of the cavitation. And biologists also said that the dolphins don't want to swim so fast as they can because the cavitation causes a pain on their skin because of these bubbles. So actually it happens because you have the fast movement of the liquid and the pressure drop, and then you have a big bubble, and then the bubble collapses. We are talking, of course, of micro bubbles, not like macro bubbles. And as a result, you have very high pressures locally, up to several thousand bars, and very high temperature, up to several thousand kelvins. And those processes are able to mechanically destroy the molecules, to turn them apart, and cause formation of different chemical reactions and the formation of different oxidants. And cavitation is lately used for the removal of organic compounds, also for the disinfection, for the removal of bacteria and viruses. But it's actually some kind of black box of the processes again, because we are not completely sure what is actually happening within such process. I have to admit that we were not very successful when we tested our antibiotics with the cavitation, because actually you can consume quite a lot of energy, because you have to speed up the liquid, you have to increase the pressure and everything. And we try to calculate some kind of specific energy consumption in different systems, but however, we were not able to achieve important additional removal of such pollutants due to adding cavitation. So our experiments were, I have really to admit, not so successful as we expected. So to conclude, for the removal of new micropollutants in different types of the wastewaters, there are a lot of processes available, but selection of the appropriate one is related to many characteristics of the wastewaters, and what we want to actually achieve. Is this the only treatment? Is this the part of broader scheme of the treatment? And of course, we have to think about the costs, especially if we combine different processes together. However, the things in Europe changed. We expecting new directive on wastewater treatment, which will also address the micropollutants in the different types of the wastewaters. So that means that the question of adding different types of treatment into our existing treatment system is something we will have to deal with. It's probably not going to be easy, and I'm sure that it's going to be expensive for all of us producing wastewater, and this is something which I know for the wastewater treatment plants in Slovenia, no one is happy about it. Okay, thank you.
Comments from the audience? Yes?
So very interesting presentation.
Thank you.
Talking about the micropollutants and your approaches to treat them, particularly these cavities, might be affected on microplastics, nanoplastics. Did you test?
Yeah, we have tested it. We have tested it, but actually we have noticed only under the microscope some kind of surface damage, you know. It didn't even go into the nanoplastics or something. It still stays there. Maybe it would add somehow if we add cavitation somewhere in the process, but actually it's not the only solution, because we have tested polypropylene, polyvinyl chloride, and I think that also PET, something like that. But no, not something that I would say that it was efficient, because it depends upon the cavitation number and the number of the passes through the system and everything. But as I said, the longer the process of the cavitation is, that means that you return the liquid back into this active zone, more efficient it is. But in the microplastic, we use like more than 200 number of passes, which is actually, laboratory option. It is not like a real option, and we were not successful. I know that some colleagues from the Faculty of Machinery, they have a larger equipment and they are more successful, but we were not.
I have one naive question.
Okay.
When they put a new antibiotic to the market, of course they need approval from the agencies.
Yeah.
But there is probably no rule that that additionally you have to also develop technology of how to treat it after it's put to the wastewater.
No, but when it's actually the life finds its way. So that means when you have a new antibiotic and it goes into some kind of wastewater, this wastewater usually goes to some biological treatment plant, and you actually immediately start to grow resistant bacteria. Yeah. So this is the reason that the only way is to reduce the application of the antibiotics, because the main idea is some antibiotics which are only used in the hospital, that simply means that the patient should collect all of their wastes to be treated within the hospital, not go to the toilet and release all of these antibiotics in the municipal system, because it will immediately go to the treatment plant and we will start to develop resistant bacteria.
Okay, thank you.
Thank you.
Thank you again. So our next presenter is Tanja Čerković-Veličković. For all those who have a fish menu for the lunch,
no,
it's a
but
it's
not only fish, not only fish.
Seafood, but I guess not
yeah,
only fish.
not only fish. Thank you, for inviting me here, for giving me the opportunity to talk about a very relevant global problem nowadays. And thank you, Andre, for giving a very nice introduction to the problem of pollution in water, in oceans, but also in fresh water, in the soil, air, etc., and of course in the food we eat. So I suppose I need to find my presentation.
On the other side, I think,
Yeah, thanks. It's here.
Just use F5.
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 Okay.
This is not working here. The remote, the laser is working, but the remote not. So
The remote is
you
not
have
working.
to use the keys.
Okay, manually. Okay. So today I'm going to talk a little bit about the microplastics apparently in foods. And this, our results and this research is part of the ongoing project that aims at understanding the health effects of micro nanoplastics, particularly in allergies and asthma. And we aim at several very ambitious goals, such as to improve the exposure assessment, to understand the relationship between the micro nanoplastics and allergic diseases, as well as to evaluate the role of these particles as vectors for contaminants, especially into the human body. And microplastics in foodstuffs is, of course, part of the exposure assessment. We all know that microplastics is practically everywhere, and only in the oceans we think that there could be more than 5 trillion microplastics circulating, with the numbers increasing with the predictions that in, maybe 70 years from now, there will be 5 times more microplastics in the oceans. Why? Because it is extremely durable. It persists practically everything. So you don't have to be a polymer scientist of a person looking into the microplastics for living, like some of us. You can just read the magazines and you get all the relevant information. Every time we find microplastics on top of Mount Everest, or maybe in Siberia in their rain, in uterus of newborn babies, then we get news. It hits the headlines of the magazines, and public is very much concerned, maybe even more than it should be. So, of course, there is a lot of microplastics, a lot of examples. I just wanted to show one of the examples from Slovenia, done by a team of Slovenian scientists. Is in 2 small rivers or springs. One of them is Ljubljanica, and the other one is Kamniška Bistrica. They have found microplastics. I think this is the polypropylene and polyethylene in fragments in amounts of around 10-20 items per cubic meter. They also have found it in the sediment. So this is the thing that is going on with microplastics. It absorbs microorganisms and other materials, and then it can settle down and become part of the sediment. It happens in oceans. It happens also in fresh water. But somehow it also gets into the soil, into the land. So we nowadays even find it in soil. Soil is also contaminated. And once soil is contaminated, then there could be transfer into plants, into the food, raw food we eat, the vegetables, fruits, and later on into the animals. Of course, we know there is microplastics in oceans, in seas, so apparently seafood is affected, but not only seafood. So going back to the definitions, maybe I should have started with this. Just the microplastics, there is a lot of definitions, but everyone says, okay, it is a particle, plastic particle that in size it's less than 5 millimeters. And also it has the lower size limit. It's only like around 0.1 microns or 0.1, we will see later on. One of the definitions is everything less than 5 millimeters is microplastics, but then Where is the nanoplastics? What is nanoplastics? Different definitions. Everything with a nanometers dimension, one of the dimensions, or everything less than 100 nanometers. It depends on from which field you come. If you come from the field of like nanosciences, you would say, okay, it is 100 nanometers because this is the measure that is the upper limit for a particle to have colloidal properties, to be really like, the true nano. But for practical reasons, we very often, even for all the submicron particles, say they are nanoplastics. And this field for us is indeed yet a black box. For the microplastics and the macroplastics, we have analytical methods. We have instruments available so we can chemically detect them. But when it comes to the nano size, we do not have proper analytics yet. So we really do not know. We live in a black box. So there is, of course, the lowest limit, 1 nanometer, 2 nanometers. If there is a molecule, so where is a polymer? From which number of units the polymer becomes? Somebody says it's like 3 repeating units, so it's a polymer. So there are also molecules, oligomers of the plastics materials that can also be found, but they are not considered the plastics. So the sources are like, from practically everywhere because we live in the age of plastics, in the century of plastics, since like, the beginning of the 20th century, with the Beckley, the first plastics patented, we live in the age of plastic. So it is everywhere, and it comes into the environment from various sources. So once it gets there in the environment, the tiny fragments that can come from clothing, from the microbeads as a primary like produced microplastics, or even from some larger plastic products, so they can start interacting with the environment. And this process of being the object of action of UV lights or microorganisms or enzymes or other different chemicals and contaminants leads to something we call the aging or weathering process. And this is a completely new layer. We already know that there is a lot of, like in chemical terms, different microplastics produced. In addition to this, they also get to have a lot of contaminants, additives, etc. Plus, if there is an aging or weathering process, we have to analyze a very heterogeneous mixture of compounds if we are the analytical chemists working with this characterization. So, of course, because plastics is everywhere and it's found everywhere, we would like to know, is there a risk to our health? And to properly estimate risk to microplastics, first we have to know the hazard itself, then we also have to know the magnitude of our exposure to microplastics. And then in combination of the two, we can properly assess. We are far from any risk assessment to microplastics. Even looking at the exposure, that should be relatively simple in any other things. We have the proper analytics, we analyze, we get the quantitative numbers. For the microplastics, there is like, it's still a black box, particularly. Why? Because there is a lack of data and proper analytics on the weathered microplastics, and when it comes to the nanoplastics, we do not even have proper analytics. So that was, in a way, something we also wanted to improve. For the purposes of estimating exposure to microplastics, and exposure scientists who work with us want to know in details the numbers of microplastics in a particular, let's say, foods. The chemical characterization, the size of that material, or the size range, and also shape, because from the exposure point of view, the spheres, the fragments, or the fibers, they have different effect, they bring different risks. And of course, it is indeed a very, very difficult field because we don't have reference materials. We still have no detection methods for small sizes. We are dealing with a lot of different chemistries. Then the matrix sometimes, it's very complex in which we have to analyze the microplastics, and the most complex ones, of course, are biological tissues as well as food. And, of course, there is this weathering of microplastics that can really hamper our chemical characterization of these materials. So one of the, speaking of our exposure, human exposure to microplastics, one of the main routes of the exposure is injection exposure. And microplastics comes from in a form of food additives, such as salt and sugar. It's also found in drinking water and beverages. It gets incorporated into the foods and the food chain in general, and it can also migrate from plastic packaging during the food processing. We, in cooperation with our partners from Science and Exposure experts from Belgium, we have conducted a survey on the occurrences of microplastics in common seafoods we eat. And because it is also relevant from the point of food allergies, we took into account mussels and clams. We also included oysters, and later on for the exposure assessment, shrimps. And the survey of the literature showed that in the past 10 years, because this field is relatively new, we can say that since maybe 2014, we can look at the analytics and the exposure assessment of microplastics in different foodstuffs. The ranges found are quite wide. So it's comes from almost a 0 to 10 or maybe 20 microplastics per gram of food. It's like 10 times or 100 times the ranges we found in different studies. Then we looked also at the analytical methodology. And nowadays, FTIR, it's a spectroscopy, is the most common method. Later on, we had some different. But even the most commonly used method has its variations, such as focal plane array, also micro, ATR, etc. So of course we wondered what is the cause of this variation in the numbers identified. Is it so that maybe in China, mussels, we have 100 times more microplastics than in Belgium or in the state? Or it's like a species-specific, or it's a method-specific variation? It's indeed very intriguing question. So first we wanted a little bit to look at the methods. And in one of our studies, we have simply compared one of the methods used for fluorescent staining of microplastics in combination. The same samples have been analyzed by FPA, FTIR, a little bit different kind of spectroscopy, simply because it functions like a chemical imaging. And we indeed noticed that one of the methods is overestimated in comparison to the other one. Even though the size range for the fluorescent microscopy could be 5 microns, and for the FTIRs it's 20 microns, we still detect less using this method. And we looked a little bit deeper into this, and we observed biological material remnants in these samples after the digestion, which means that there is a lot of false positives if you are using fluorescent microscopy on the basis of Nile rate staining. Okay, but we were also not happy with the results we got with the FTIR. Why? Because the biological material remaining on the microplastics can also hamper the chemical characterization. And we understood that absolutely the most critical thing to improve the exposure assessment would be to go back and to improve the extraction procedure and the preparation of this sample for the chemical characterization. So briefly speaking, we looked into the protocol that could eliminate the matrix, have no impact on the particles, will not introduce extra contamination. It's also time efficient, cost efficient, etc. And we came up with an improvement of the digestion procedure for this biological tissue in question. We combined the alkaline hydrolysis, which is commonly used, for a while. Then we transfer the remaining material on the filter, and then in situ we have conducted a 2-step enzymatic digestion to kind of mimic gastrointestinal digestion that combines two enzymes, the pepsin and the pancreatin, and it's very efficient. And then we had also to include a hydrogen peroxide in the final step. It's a bit of the oxidation, but relatively mild with only 15%. Why? Because before this oxidative degradation of the remaining materials, we actually had a lot of, see this yellow, red stuff is what we don't want to see in combination with the microplastics, because these are some extra biological materials, so our filters were very clean. We also estimated the digestion efficiency, and we noticed 99.8% in these three different species, not less than 99.65% in any of the replicates we had conducted, practically the highest seen in the literature. We were extremely happy, and then we started looking by using micro FTIR on the real samples and the filters obtained. So the first, column here is the average number of particles we could see and count using the microscope. It's a whole filter coverage. It's around 1,000 in all of them, like different mussels, clams from different regions. In our study, we combined 3 different point of sale markets, the Korean market, Croatian market, and the market in Belgium, as well as the Serbian market, even though we don't have the sea. And then when we allow the software to count the microplastics, out of 1,000 particles seen, it counted around 20. Then with a better match, we wanted to increase the threshold for the recognition to be more sure about what we identified. We got only 2 plastic particles out of 1,000 particles we have seen on the filter. And with the manual verification, expert in FTIR just checking what the software identified as a plastic, we came down to around less than 1 particle of microplastics per filter. So now you little bit understand why this is so analytically challenging. You're looking for a needle, in this. It's with the highest efficiency of digestion, the cleanest filter possible. We still have 1,000 of garbage on the filters. And the one thing is the one we are looking for. So not really, really challenging, I have to say. Anyhow, at least we have standardized our digestion and our spectroscopy, and we could now analyze the whole collection of samples. We collected samples from different markets. We now analyze them manually. It took 1.5 years for both person digesting and the other one doing chemical characterization. So at least we can say in one laboratory using a very standardized condition, we minimized all of the variations, so we can say, okay, do we see any region differences in the samples or any species differences in the samples, and compare these results. Well, you can see that the numbers of the particles we have identified, it's not so dramatically high. We can say that there is a low exposure to microplastics consumption in the food samples analyzed. We have noticed, let's say, that shrimps have less microplastics than other species tested. So regardless of the point of sale, is it the South Korea or Europe? But a big bet is we can be sure about what we have seen and counted for the plastics that has size of down to 40 microns, because this is the analytical limit of our method. We have been using the spectroscopy. FTIR has a lower limit of detection than 20 microns, but we have been using it in the reflectance mode, which means that we needed at least 20 microns of the surface to be reflected, and the particles are irregular. So in reality, it is a particle of 50 microns that is the lowest we could detect. So we don't know anything about smaller particles, about nanoplastics, absolutely nothing. So we cannot say much. But for sure we can say that the standardization of all these steps is absolutely necessary. It's urgently needed, because otherwise we will never be able to estimate the real magnitude of the of the exposure to this micropollutant. I think that's all what I wanted to say, and I'll be very happy not to give answers to your questions. This is the team from Belgrade, also from Brussels, Croatia, and from South Korea who participated in this part of the study that I today presented. And of course, thank you very much.
Thank you, Tanya, for shedding light on these and telling us how important it is to be careful with analytics.
With analytics,
Yeah.
extremely
so,
careful.
Any questions, please?
Should we eat fishes or not?
Well, you should eat shrimps and oysters. Yeah, absolutely. I did not actually look at the fish, did not mention, but we know that in mussels, in clams, because they are like pretty much filtrating all this water, they collect a bit of more microplastics. And in fish, if you remove the digestive tract, the fish meat is not so contaminated.
Does it only thank you. To go on in this direction, does it only concern sea fish or also river fish?
We also found microplastic in fresh water in the river, so it's also everywhere. And in my opinion, it's not just the microplastics which should be worried about. The chemicals associated with microplastics are something to actually worry about. The phthalates, the residues, and the microplastics, being plastics very hydrophobic, can concentrate very hydrophobic compounds, pesticides, some antibiotics. So they are like bombs for our organism. Once you get it, they bring very high concentration of unwanted chemicals concentrated in a small size, especially if it's nanoplastics. It's really like, so not the plastic itself. It's chemically inert, you can't degrade it biochemically, you can't do much to plastics, but it brings a lot of things with it, even like toxic metals.
And your research does not concern nanoplastics.
It does concern nanoplastics.
That is a black box. Because I heard in the academy at another conference that nanoplastic is unbelievably dangerous from a medical point of view because these particles can enter cells. And that may be very dangerous for cancer and things like that, tumors.
I did not want to expand this into the nanoplastics. Of course, we do research on nano, but we model nanoplastics. We make nanoplastic in the lab, so now we can track it, and we know the smaller is the size of the plastics, deeper it can go into our body. So less than 150 microns, it can enter through the digestive tract. It can be taken up, but then there is a blood-brain barrier that nanoplastics can cross, so it can get into brain, etc. So that's why, because it can really penetrate everywhere, we had to have a very special focus on this. But analyzing toxicity is something really difficult. Also, you make something in the lab, so how sure you are that there are no contaminants present there that can be inflammatory, and any inflammation is cancer. Any more questions? Yeah. I think.
Did you have maybe some problems with the contamination in the lab? Because we have a lot of problems with the fibers and everything.
Yeah, absolutely. No, we we always set up 5 samples that we analyze, and we have one control, a blank sample that has to go. Everything is like a procedure control. We have no contamination. But we have a special lab for microplastics. That was the first thing that we established in a very specialized place to work there. Then there are rules like clean food, the cotton, hair, a lot of things to, when it comes to the quality control for microplastics, there are 5 basic rules that you have to fulfill, and we fulfill all of them. Not all of the studies, in fact, fulfill these criteria. material, we know this. So not everything you read in published paper comes from a clean lab. So that's why we really cannot estimate the exposure. We don't know where are the sources of error, from where it comes, the contamination, the too low threshold in spectroscopy, inexperienced treatment of the samples, counting biological material instead of the microplastics, or who knows what. Yes, please. If we can, I made it short. Yeah.
I want to thank you for this highly reflected speech about microplastic. And what comes in my mind, it's a typical example for this secondary effects of Anthropocene and for the tertiary also, because my feeling about that is it could be dangerous, but we do not know anything. It's a complete black box. We know, meanwhile, it's disappeared all around the world. We know it can go into the smallest part of the body, in the cells, but we actually do not know what it's doing. Maybe it's harmful. It's no problem. Maybe it's harmful. We don't know. What do you think about
We
this
should be cautious.
What do you recommend? What can we do?
Yeah.
What should we do?
It's a lot of discussion also at the European Commission level. And at the moment, a very new thing is there is a new legislation on the microplastics. So the primary microplastics, like in cosmetics, etc., is now banned. Then there is microplastics might be on the watch list for drinking water, and the GRC, the Institute of the European Commission, is developing the standardized protocol and the method that we should be applying to enhance this. So we are watching. We started looking at this. We still do not know. I cannot be sure about any health effects. Really, in the last few maybe months, I have seen few relevant applications that we might consider as something like to start looking deeper into this. There is a lot of microplastics in the oceans, and we know how fishes they need to reproduce by injecting the sperm cells into the ocean. So there is microplastics. It somehow kills the energy of these moving cells. So we have the fertility goes down for that. And that is a thing that we should work about. That's the first thing. And everything is somehow connected. Less fish, then less food coming from this. And still for the human body, we need to investigate a lot of things before we can say for sure there is some effect. But for the ecotoxicology, we can measure. It's a bit easier. It's all
Thank you very much.
Thank you.
We have two more presentations today, but we will make a coffee break now. So in order to have the presentations after that. So it's 4:15. I suggest we reconvene in 20 to 5. So we would have 25 minutes. Okay, now two more presentations after that. again for being here. The next talk is on the biodiversity in Bulgarian sector of Danube River. It will be presented by Ina Aneva. So Ina, the stage is yours.
Respected academicians and professors, I am glad to have the opportunity to present you some aspects on a topic dedicated to biodiversity of the Bulgarian part of the Danube River. My name is Ina Aneva and I'm Scientific Secretary of the Division Biodiversity, Bioresources and Ecology of the Bulgarian Academy of Sciences. The Danube River is often called Europe's backbone of biodiversity. The natural ecosystems along the Bulgarian part of the river are also considered extremely important as hotspots of natural and semi-natural biodiversity and priority conservation areas. In its lower stretches, the Danube River passes through large lowlands and remains an almost intact natural ecosystem. The flora and fauna of this specific area is not far from the Danube Delta ecosystem. There are no dams or other significant hydrotechnical infrastructure on the mentioned stretch of the river and downstream to the Danube Delta. Therefore, there is nothing to cause a barrier effect to migratory fish species or other animals. Unfortunately, fish migration is already a rare occurrence in many of Europe's largest rivers due to human alteration and physical barriers. In the course of the second half of the last century, wide spaces of floodplain have been diked and converted into agricultural fields, fish ponds and territory for hybrid poplar plantations. The river is very rich in small to large-sized islands and archipelagos that are mainly covered by diverse alluvial forests. These island forests are flooded by river water for 4 to 5 months in the spring and summer, and many small swamps and channels are formed inside the islands, creating excellent conditions for spawning of many fish species. These remote places are also of great importance as feeding grounds for many birds and mammals and living along the river. The depth of the river is highly variable with the complicated relief, offering many bottom thresholds and pits. When the water level is low, many small sandy or gravel islands and sand pits appear above the water. The shores of the river are often covered by riparian forests, which floods during the spring and summer when the Danube reaches its highest water levels. These forests are dominated by species of genera Salix, Populus, and in the rare occasions some Ulmus levis, Fraxinus oxycarpa, and Quercus robur. Unfortunately, forestry practices along the river and also on the islands have led to significant forest degradation and alteration of the primary forest into forest plantations, mainly dominated by hybrid poplars. Nevertheless, approximately 40–50% of these forests still represent primary habitats and continue to hold great importance for the preservation of rich biodiversity. And here you can see one of the few examples of an old white oak still growing on one of the river's islands, but in Ireland. The largest area of typical alluvial forest can be found on Persin Island, the Kalimok Island complex, Vardim, Aleku islands. Like the forest, the wetlands ecosystem in the Danube's lowland have also been negatively impacted in recent years. Drainage, water and air pollution, poaching, fish, birds, mammals, illegal logging, rural and infrastructural development, and hydrotechnical construction are among the biggest threats, both past and current, to the wetlands. Between 1920 and 1970, a great majority of the Danube's marshes were drained for agricultural development. Marshes covering thousands of hectares disappear from maps together with their impressive and rich wildlife. In addition, dikes constructed along the river around Persin Islands in the middle of 20th century led to the degradation of wetland areas as they were gradually cut off from the river. The river dikes also instigated a process of rapid secondary degradation and eutrophication among many of the partially remaining wetlands. The largest part of the new plain included in the study area is covered mainly by agricultural lands, steppe vegetation, oak and silver lime forest. Many of the Danube's right tributaries, including the rivers Lom, Ugosta, Iskar, Vit, Osam and Tiantra, also cross this plain. These river valleys are key for biodiversity and maintaining green corridors. There are three maintained reserves, Srebrna, Ibiša and Persinski Blata. Srebrna Lakes is also Biosphere Reserve, a UNESCO heritage site and an object of the Ramsar Convention. Recent studies have shown that the Bulgarian sector of the Danube River and adjacent territories hosts more than 3,000 taxa of algae, 200 species of macromycetes, more than 600 species of vascular plants, and several thousands of animal species, most numerous being invertebrates and particularly insects. There are 83 species of fish, some of them of high conservation concern, including the 6 sturgeon species. Mammals are more than 70 and many of them are rare and protected. The following vascular plants have restricted distribution and are threatened at European level. There are other species which have limited range only along the Danube River and are closely tied to the river's habitats. Here some examples: Tragopogon fulcosus, Achillea ochroleuca and Rindera umbellata. A total of 67 mollusk species, 47 gastropods and 20 bivalves, which presents about 13% of the Bulgarian mollusk fauna, have been reported in the Bulgarian sector of the Danube River. The reported species belong to 14 families, and the highest species richness was recorded in the family Planurbidae, followed by Spheridae and Limnidae. The main threats to the mollusk fauna in this part of the river are the same as the globally known major threats to freshwater biodiversity, including loss and degradation of habitats, overexploitation, pollution, introduction of invasive alien species, and climate change. throughout the years, the water of the Danube River have been contaminated by different sources used in urban agricultures, and the ichthyofauna of the lower Danube, including the Danube Delta and its food plains, has been characterized by high species diversity. A total of 83 fish species belonging to 21 families have been reported. Of these, 69 species are native for the Danube River basin and 12 are alien and introduced. The status of the 2 species is still unclear. 8 species are considered endemic in the Danube River basin. The family Cyprinidae is represented by 35 fish species, which is about 42% of all fish species here. And the native herpetofauna is located 10 kilometers south of the Bulgarian Danube River, comprises a total of 34 species, 15 amphibians and 19 reptiles. Although the main channel of the Danube itself is not optimal for most of the species except for the natrix species, the river shapes and impacts various aquatic habitats of great importance to the herpetofauna. There are 74 mammal species registered on the Bulgarian part of the lower Danube area. The European ground squirrel Spermophilus citeus is closely associated with pastures since wild in Pleistocene and domestic after Holocene, and made an optimal for the species grass cover structure. In recent decades, pastoral farming is in ingress, and which also contributes to the reduction of population of species. Today, the European ground squirrel is a vulnerable species. The same situation is to marblet polecat, Vormella peregusna, listed as vulnerable in the IUCN Red List. It's another rare and cryptic mustelid species whose distribution in Bulgaria is known mostly by accidental registrations. There are some formal records in the eastern and central parts of the Danube area. Lutra has specific habitat requirement. It is spread along the banks of running and stagnant waters. In the recent past, the main factors contributing to decreasing its numbers are human persecution and water pollution. In recent decades, the population has recovered. The grey wolf Canis lupus, which is rare in the lowlands of the country, is known to appear in low numbers along the Danube River. The Danube River provides some suitable lowland habitats for the red deer, but unfortunately the red deer population has declined critically in the region, mainly due to poaching. The region is characterized by a great diversity of riverine habitats and habitats directly influenced by rivers' proximity. For example, the habitat of Pannonic inland dunes is only present in the Danube lowlands. The other Pannonic sand steppes is one of the rarest habitats of the country. The rich biodiversity along the Danube River in Bulgaria is protected in different categories of protected territories. There are 2 nature parks, 6 nature and maiden reserves, numerous protected sites. Natura 2000 network is represented by 25 zones. declared according to the Habitats Directive, and 11 zone declares according to the Birds Directive. However, the rich biodiversity in the region has faced serious issues over the years. Still, in the first half of the 20th century, many wetlands near the Danube River were drained and converted into agricultural land or fast-growing copper plantation, drastically losing biodiversity. Environmental pollution, including transboundary ones, biological invasions, change in the water regime, improper management and use of natural resources, and other negative factors of local importance were joined by a global factor, climate change. All these challenges can hardly be addressed at a national level, and therefore the international cooperation of the Danubian countries is of crucial importance for mitigating and reducing the effect of the negative factors and for making a step forward in conservation of this fragile and extremely valuable ecosystem. And thank you for your attention.
Thank you. If somebody has something to comment or ask, feel free. Yes?
I would just like to ask you, what is the most urgent task you should have do in the protecting the biodiversity now in the northern region?
First of all, to change our way of thinking. It's really long term. To think more ecologically in this point of view, because many people doesn't think about the ecosystem at all. They just want to see green forest and growth popular that are fast-growing species because they are green, nice tree, bigger, and produce oxygen and so on, and wood. But the task is really difficult, and ecosystems are more complex, and every species has its own place there. And,
my question about numerical barcoding. How often we use these methods for what species of plants, maybe animals?
DNA barcoding, but it's part of the other project. My research interests are mainly in the field in medicinal plants, but I am a scientific secretary of Division of Biodiversity, and that's the reason I present this topic. But DNA barcoding may have many applications, and to distinguish species that are morphologically close to and similar, so similar. And, for example, one example of medicinal genus Thymus, you know Thymus of Lamiaceae. In Bulgaria we have 21 Thymus species that are so close and similar and look so to each other. But when we applied some genetic markers, we can distinguish them on molecular level. And now it's easier.
Thank you again.
Thank you.
So we came to our last presentation. It will be given by Dmitry Grumov from Belarus National Academy of Sciences, and it will be a presentation on the peatlands restoration. So we'll just put it on wetland restoration. I think this is one.
Dear colleagues, my presentation about important problem in our country of water conservation. Peatland restoring experience in Belarus. Few words about our country. Belarus situation is geographical center in Europe. In general, the relief is low. Belarus is country of forest, mares, lakes and rivers. The watershed between the Baltic Sea and the Black Sea pass through on the Belarus territory. The largest rivers in the Baltic basin is Western Двина, Neumann, and Western Bug. This is Baltic basin. The largest river, the Black Sea basin, this is Dnieper, Pripyat, Berezina, and Soch. Peatland on Belarus are one of the most important part of the hydrographic system. Many rivers begin from peat bogs. General peatland information. Belarus is one of the most important countries of the world peat. 15th place in the world on the peatlands total area, 20th place in the world by swampy on the country area, 21st place in the world on the actual carbon stock. Our peatlands, this is fen, raised bog, swamp, and transition mire. This is information about situation before large-scale drainage. We have next situation. The north part of Belarus, named Poezeria, represented by lakes, bogs, and river. Central part represented by agricultural landscape. In south part, named Polesia, is represented by broadly fence, transition wire, and fence. National symbol our country, the book People on the Swamp, is about life in Polesia before drainage. People live on Iceland between swamp. Belarus wetlands are unique, beautiful formation. For example, Yelnya box is 5th largest raised box in the Europe. Almany Myers, the largest in the Europe complicated complex of box, fence, and Myers. Preserve former military training ground, Merlinskaya Hutara, second in world training ground. Pripyat Mire, last natural complex of box, fence, and mire. Now reservation in Pripyatsky Natural Reserve in Polesia. Kaziansky bog, unique, hard to reach raised bog in the north of Belarus. Zvanets, one of the 3 largest mires in Europe. Sporovsky mire, floodplain home to Europe largest population aquatic warbler. We joke that this is one most expensive bird in Europe. And Dikoya mire, the most titled mire in Belarus, it may be in Europe, a UNESCO World Heritage Site and a number of international protection status. About history, large-scale drainage for the agriculture, forestry, peat extraction needs was in Belarus in the 1960-1980. But 1990s, large-scale drainage was stopped. Now situation, former extent of peatland is more than 12% of the country. Present area of natural peatlands about 4% of the country. In our area of draining peatlands, more than 66% of the peatland area. Look this change of natural peatland area during the drainage and peat extraction in Belarus. Before drainage and modern situation, raised bog, transition mile, and broadly fence and mire. Now situation next and black degraded peatland. For everyone, for our country, wetlands is water, biodiversity, natural resource, and community well-being. For example, 7 billion cubic meter of the fresh water now safe in peatlands of Belarus. The problem of degraded peatlands. No, emission of greenhouse gas as a result of peat mineralization, peat fires, reduction of biodiversity, problem of hydrology, about from 5 to 7 billion cubic meter of water lost during drainage. Peat fire national problem in the past. South of the country was the most intense drainage, now a problematic fire dangerous area. And one more problem, radioactive contamination after the Chernobyl incident localized here. Was this territory? Is this incident pollution, radioactive pollution zone? Biodiversity. Wetlands, the place of conservation globally key biodiversity, the 30% the National Red Book inhabited on the wetland. And wetland restoration practice. Now, since 2006 year, 40% project area restored in Belarus in total area of 17,000 hectares. How we select object to restore? A layer of peat at least 30 centimeter, dry peat. The peat bog can be swamped to the level of the surface. The area is not agricultural land. The area is without shrubs and forest. Restoration of peatland carried out by overlapping cascade drainage channel. This is dump drainage channel and dump every year. Example, dam construction example, plastic dam, plastic stone dam. This is our experience long time. Anti-filtration dam, seal dam, an example of volunteer handiwork, material woods, from woods, seal dam, complex dump on Yelna Bog, is plastic dump from peat, peat dump from excavator formation, overflow dam. What's happened after dam construction? We can see the main recovery phase. This is best result of the experiment for fence. First step, bar pit, from 1 to 5 year, first plant epi, fragments, carex, area forum, and more 10 year vegetation with area forum, carex, fragments. But for fence, usually most common result. Fan, open water, and communication with dominant fragments or tifolia. For raised bogs and transition mire, the dynamic of vegetation restoration are long, at least 40 to 50 years. All our practice in the basic in the law protection and use of peatlands, the first in Europe. Very important part, ecological and socio-economic effect of peatland restoration. No, this is practical effect. The main effect, decrease in the number and the and the area peatland fire a result of wetland restoration. Look this example for north of part of Belarus and dynamic peat fires before and after restoration. Our research pay great attention to the ecosystem service calculation. This allow to monetize effort to degraded peatland restoration. First, the most important indicator is the cost of fresh water accumulated in bog, cost of cranberry harvest, the cost of reducing greenhouse gas emission. This is monetized effort of degraded peatland restoration. Way to use restored peatlands. No, we have 5 directions. Creation of protected area, territory, restoration wetland, an object of ecology tourism, very popular in our country now for ornithology, tourists. Production of plant biomass from restored area, nice fuel, compost, paper, packing material, and other. Harvest of wild and cultivated boxberry medicine plant. For example, it's a real situation in bog restoration for cranberry harvesting for local people in south of Belarus. An ecology festival every year, is very popular now. Prospect for wetland restoration for the future, a roadmap for the peatland restoration has been developed. We have calculated restoration indicator, restoration degraded wetland ecosystem, reducing greenhouse gas emission, freshwater reserve, area K biodiversity, restoration protected biotope, reducing the risk of peat fire. We have planned to restore a natural riverbed. Thank you. Sorry for my English. Thank you.
Thank you very much. I know that you wouldn't like questions, but if there is something, feel free. Yeah, there is one. There is one.
I have a question. First of all, let me thank you for this very good example that things can go in a good way also, because this drainage of wetlands is extremely sweetening us, and I already did absolutely not know that in Belarus these regions exist, and especially that you are on the way to recover the regions. And in this point, I would like to ask you if we or I can get the slides or some slides that we can spread this news. I don't know if it's possible that we get your slides that we can report at home about these good ideas for recovering the wetlands. So thank you very much.
Probably you should contact directly to discuss about my stroke. This concludes the session, so I would give word to Professor Stanoni for concluding remarks.
Thank you very much. Ladies and gentlemen, the scientific part of this conference is coming to the end. Sorry. So the scientific part of this conference is coming to the end. At this conference, 12 oral presentations were given and one video or half video contribution. The first part in the morning It was dedicated mostly to karstic regions along the Danube River. In the afternoon, the communications were dedicated to some technology of water purification and also biodiversity in Bulgaria and some problems of peatlands in Belarus. So in this conference, 6 countries were participating, and this is Slovenia, Slovakia, Serbia, Bulgaria, Belarus, and Montenegro. I would like to thank all the speakers of this conference and also all those who were participating in the discussions. At the end, I would also like to thank the members of the organizing committee, the co-chair, Professor Franci Gabrušek, then Mrs. Anja Miljavec, Zoran Mezek, and also to ROK Letonia. So thank you very much, all of you. And about tomorrow excursion, all those who will go to Postojna will be picked up at 9 o'clock, as I understand, at Hotel Slon, and Professor Franci Gabrušek will guide you from Ljubljana to Postojna and through Postojna caves and so on. So thank you very much.